Good morning, everybody. Can you guys hear me all right? I'm hoping so. My webcam fell, so I'm not sure about the positioning. I guess that looks fine. You guys can see and hear me all right? Thumbs up? Yes? Perfect, perfect. So, are you guys excited? Are you guys excited for reading week? I guess it doesn't really matter too much when the class is just once a week, but nevertheless, reading week is always nice. I'm sure that you guys have some fun plans, or maybe at least would have had some fun plans before the pandemic. Do you guys have any plans for reading week? Anything fun going on? Nope. Yeah, well, that's okay. I don't either. I guess next reading week. Sleep, yes. Sleep is very, very nice. I miss sleep. Ever since my apartment flooded, I have contractors coming in at 8 a.m. every day. So even on my days off, I still got to wake up early, which really sucks. Yeah, too cold outside too. Yeah, it hasn't been that nice out. Canada caught up with us. It was looking pretty good at the beginning of January, but that's usually a trap, I find. If it's good in December and early January, ooh, watch out for February. All right, so before we begin today, we're just going to kind of take a step back and look at what we've done so far in the course. So we started with linear algebra. We took that knowledge from linear algebra, even though it seems pretty useless, and we actually applied it to something, which was solid mechanics. That allowed us to derivate a bunch of things like the strain tensor, stress tensor, stuff like that. From there, we were saying, all right, well, now that I know all these things about stresses and strains, I can find exact solutions, which is what we did for an Euler-Bernoulli beam. From there, we said, all right, well, these exact solutions, they suck. No one wants to do exact solutions. You have to solve a differential equation. That's for first years. That's not for us. We're graduate students. Who cares about differential equations? So we introduced some approximation methods, which allowed us to basically obtain approximate solutions to all those differential equations that we had before. And we said, all right, let's take it a step further. And instead of solving for an approximate solution for every single point, why don't we discretize our problem into simple one-dimensional problems? So in lecture 4, we introduced the finite element method in its most simplistic case, which was a 1D bar element. So that was just something that can be stretched or compressed. Nothing too special, right? Now, I'm just going to adjust this really quick. My question to you guys is, how many of you guys are mechanical engineers or material engineers or even chemical engineers? Basically, how many of you guys are not civil engineers? All right, so we got a mechie engineer. Anyone else? I know you guys are out there. All right, another mechie. So Maddie, mechie. So basically, we have a lot of engineers in this course that aren't civil. But up until this point, we've mainly been focusing on beams and bars. Now, going back to beams, though, or the Bernoulli beam, that's more of a civil aspect, right? You guys probably don't deal too much with big, long, 10-meter span beams. That's more civil. So the question is, why are we focusing on beams and we have so many mechies? Well, of course, we know that the finite element method isn't just limited to beams. And that's why today is so special. Today we're going to introduce an element to you guys that everyone will use. So if I were to type in, just randomly on Google, finite element analysis, and go images, you guys are probably expecting something like this, right? You guys weren't expecting just beams and bars. This is what you guys came here for. This is the juicy stuff right here. Now today, guys, today we are going to look at how to get these type of elements, which we call solid elements. Now what's great about these solid elements is they can apply to any situation. Look, I don't know what this is. I'm sure my mechie guys can help me out with what that is. Whatever this is. You guys can do a wheel if you guys are feeling brave. But basically, after today, you guys will have the knowledge of a very powerful element. Very powerful element that you guys can use in any situation. You guys are feeling brave? Model a plane. Why not? That's the power of the finite element method. So this should be a really fun lecture. Now, after we are done this lecture today, we're halfway done. So the contents of this course go up to lecture 10. And if we're done lecture 5, well then, yeah, we're halfway there. Which is great for you guys, right? You guys excited? I can't believe how fast it's going, if I'm being honest. I felt like just yesterday we were just starting out. So after today, we will learn that very powerful element. And by the end of today, you guys will actually have the knowledge of the finite element method. What we do after that, so in lectures 6, 7, 8, 9, and 10, is we are going to take the finite element method that we know right now, and we're going to start tweaking it to make it more powerful as well as run better. So this right here, lecture 6, isoparametric elements, this is actually the same thing we are going to learn today. We're going to learn today about that very powerful element, but we are going to see that it has one big problem. So what we're going to do in isoparametric elements is we are going to address that problem. So we're not going to actually introduce anything new. We are just going to address a problem of FEA in 2 dimensions. So basically that solid element that we're going to do today. Lecture 7, well, we're going to say, all right, well, our system right now, we know how to solve because it's just a linear system. It's not too bad. But what happens when that system becomes nonlinear? I'm sure that you guys know that not everything behaves elastically. So let's say that we have concrete where it has a parabola as a stress strain curve. Well, how do we solve that? We can't just put it into a matrix and say we're good the entire time. So that's what we're going to introduce in lecture 7, something called the Newton-Raphson method. After that, we go into material plasticity. So again, we know that materials aren't always linear elastic. Up until this point, all of our calculations have been nice linear elastic functions. So they're actually very easy to solve. However, that's not the case in reality. We have to deal with things like strain hardening in steel. So after it yields, it still has some capacity. The slope just decreases. In concrete, we deal with it cracks in tension. And we also know that it is parabolic, or mostly parabolic, in compression. So how do we account for those type of things? So we're going to do that in lecture 8. Lecture 9, this is the juicy one, constraints and contacts. So a lot of mechy engineers in here, this is one that you guys will probably like. Everything that we dealt with so far has either been a single beam, a single bar, but what happens if we have multiple things? Well, that gets more complicated. But what makes it even more complicated is what happens if we have multiple things that start touching each other? How do we make sure that we can account for the fact that they make contact with each other and not just go right through each other? As we'll see in ABAQUS, if I don't define contact, what happens is if I were to press 2 things together, they just go right through each other. We actually have to define that contact between them. And then from there, we go into instability. So this goes more to my steel guys. We deal with instability in steel a lot, whether it be global buckling or local buckling. It's something that we have to account for. Now, another thing that we're going to talk about in instability is softening. So of course, in design, we're mainly concerned about serviceability and the ultimate limit state. But we got to keep in mind that when we're actually dealing with failures, there is a softening portion. For concrete, for instance, we know that the curve goes up, but then we also know that the curve starts coming down. How do we capture that part where it's actually coming down? That's going to be very important. Now, my question for you guys really quick is, in design, we don't really care about that softening too much. What is one instance in design where we do care about that softening? What do you guys think? Am I teaching you guys something that's going to be rather useless, or is there an actual method to my madness, if you will? What do you guys think? Something where softening would be considered very important. Ah, good one. That's exactly what I was looking for. Seismic behavior. Because keep in mind that when something comes up and it starts coming down, it's still deforming. And that area under the curve, we said, was related to energy. So when we're dealing with something like concrete, that area under the curve is the dissipated energy from an earthquake, perhaps. So that's why it's very important that we're able to capture that, because we need to start figuring out what the ductility of our system is. And even though it's not right in the design codes, like what is the ductility, we account for that ductility using reduction factors. And those are based off of softening. So those are some applications that we're actually going to need to know. So hopefully you guys are saying, all right, well, maybe this course is actually useful, at least somewhat. So another thing that I have posted now is final project information. No one reminded me last week to do it, but that's okay. I remembered this week. So again, the goal of the project, solve a problem in which you need finite element analysis. If I were to give you guys a simple beam, Okay, an elastic beam. That's a cantilever beam. One end is fixed, point load at the other end. Do you guys need the finite element method for something like that? Or could you guys solve the beam for the stresses and the strains? Elastic cantilever beam. What do you guys think? Do you guys need the finite element method for that particular scenario? Nah, yeah. Sabrina's right. Nah, of course not. We know classical theory. The project wants you to solve a problem in which you need the finite element method. So take concrete, for instance. We know that its compressive behavior is different than its tensile behavior. We also know that once it reaches a certain limit, it cracks, which kind of sucks, because it leads to a lot of instabilities within the finite element method itself, but we're going to talk about that. But if I were to give you guys the same cantilever beam, so fixed on one end, point load at the other, but I told you guys it was concrete, could you guys solve that using classical theory? And I'm not just talking about moment capacity. I'm talking about the stresses, the strains, the crack distribution, all that stuff. Could you guys do that by hand right now if you guys wanted to? Would take very, very long. Yes, take very long. So that's what I want you guys to do. I want you guys to figure out a project in which you guys are thinking, you know what, classical theory, Mathematica, that's going to be too much, too hard, too complex. So it could be anything you guys want. And don't be afraid to get creative. There's been some really good projects in the past. One of them was the deformation of the strings in tennis rackets once the tennis racket makes contact with the ball. That's a very nice project. Now, if you guys are saying, well, you know what, Clayton, I can't really figure out a project, it says right here, this is the most important part. Don't be stressed. The finite element method, it's a very beautiful thing. Very beautiful thing. Causes a lot of pain, but it's still very beautiful. Like a relationship. I had to throw that in there. So if you guys can't find a project, or you guys can't think of a project, well, don't worry. Just come talk to me, and we'll figure one out together. So the key here, don't be stressed. Please don't be stressed. I'm sure that a lot of you guys have very creative projects, which is great. And I'm sure a lot of you guys will just use your research projects. That's another thing. A lot of you guys are doing MSCs and PhDs and MEngs where you guys have a research component or a capstone component. And sometimes, or actually most of the time, that involves analytical modeling. So a lot of students actually use this course to get a head start on their analytical modeling. It's great because you guys can do this class, but also your research for the week. Kind of put it together and you're good to go. So you guys may be saying, all right, Clayton, well, sounds pretty open-ended. Oh, another thing I should guess. What kind of finite element program can I use? Any finite element program you guys want. All right? So if you guys want to do ANSYS, go ahead for ANSYS. You guys know I don't like ANSYS, but go ahead. If you guys want OpenSys, go ahead and use OpenSys. I'm not going to discriminate on which program you guys use. Now, of course, everything that we're going to learn in this course moving forward, so material plasticity, contact, instability, I will teach you guys all of those through ABAQUS. So there is one drawback of using something like ANSYS or OpenSys, is that I won't be able to teach you guys, or at least from the lectures, you guys won't be able to see. Now, of course, if you guys have general questions about, let's say, OpenSys, well, just come talk to me. Of course, I'm here to help. I'm not going to turn you guys away. But from this lecture, you guys should have everything you guys need for the project that you guys want to solve. So another thing, too, is when I say any finite element program, sure. But make sure that you guys are able to answer what is requested. So the project is going to be just a simple report in paper format. So I take it that most of you guys have written a conference paper before, or some of you more depressed people have written a journal paper. Journal papers aren't as fun, but you guys know what I'm saying. We're going to have it in that sort of format. One, it's going to need a title. And you guys are saying, Clayton, well, of course it's going to need a title. You guys would be very surprised how many people don't throw in the title. Second, going to be an abstract. All right, an abstract. Kind of wrap all your project into one nice paragraph. Keep it concise. Okay? Abstract shouldn't be more than a page long. At least, please. I will admit I'm not the best reader. So Abstracts should be concise and contain all relevant information. After that, we're going into the introduction. This is where you guys want to introduce your problem. If you guys are saying, well, you know what, Clayton, I'm modeling the crack propagation of concrete beams. Well, that's your problem. But why? Why is that important? That's one of the hardest things I find with students in research, is they have no problem saying I'm going to do something. But you guys really need to emphasize why we're doing it. Why is it going to be important, or what difference will it make? Why is it going to be useful? As well as the objectives. All right? We need to deal with these objectives. You guys have to tell me what exactly it is you're trying to achieve. If I'm doing that concrete beam with the crack propagation, what am I after? Am I after the moment capacity, the shear capacity, something like that? And then we get into 4, which is the methodology. Now, of course, these aren't really section titles. These are just what needs to be included. So you guys don't actually have to use these as section titles. But this part right here, this is where I'm going to really look, because the goal of this course isn't to make you guys experts in ABAQUS or experts in ANSYS, because it takes a while. It's like any skill. You have to keep practicing, trial and error. So by the end of this course, I don't expect you guys to become experts in a program and get perfect results. It takes a long time. So what I am looking for is you guys take the things that we learned in this course and apply them. So first thing I want, problem geometry. If you guys are modeling a beam, I'm going to want to know the dimensions of the beam, stuff like that. Material properties and mechanical models. This is important. Again, later on, we're going to talk about plasticity models. And we're going to realize that under certain plasticity models, we're going to have to use specific element types. So it's things like that where I'm going to look at, all right, how do you guys approach this problem using what we've learned in this class? That's the whole goal here, is to see what you guys can take from class and apply it to the model and even extend what we've learned in class. So things will include material properties, element type. As we're going to see today, there are many different element types. Element size, which is related to mesh sensitivity. As you guys know from the linear bar elements in your guys' assignment, if we were to do smaller elements, so more of the elements, the results get better. But there comes a certain point where the results are basically the same. So how do we know that when to stop? I keep decreasing my element, my results start to converge. How do I take a step back and say, you know what, this is good enough? I don't want more computation time. So it's stuff like that. Loading and boundary conditions. This is going to be fairly straightforward from your problem, but how do you apply them? So one thing about loading is, are you guys going to do displacement control or load control? That's something we're going to talk about. And then the type of analysis. As we know, we've been dealing with static analysis, but that's not the real world. The real world has dynamic analysis. Or I guess it's dynamic in general, because we have inertial effects. If I were to move something, it just doesn't start moving. It has that inertial effect that resists the movement. And then from there, after you guys discuss your methodology, what are your results? So you guys are going to say, all right, well, this is the load displacement curve ABAQUS gave me, and you're going to interpret it, which results in a higher moment capacity or higher shear capacity, whatever you guys want. And are these expected? What happens if you guys get results that make no sense at all? It doesn't mean that they're wrong. The question is why are they different than you expected? Why or why not? Or are they the same as what you expected? Are they reasonable? Stuff like this. This right here is the problem with journal papers. Those of you who've written a journal paper know exactly what this why is. They say that to everything. Here's my results. Why? I don't know. I just got the results. And then after that, just conclusions. So again, just be specific. It's like the abstract. We want to keep it nice, short, and sweet. And we want to address the objectives that we listed up in our introduction. And then, of course, references. So if you guys use any references, please include references. Should be nice and fun. So is there any general questions about this project? How are you guys feeling towards this project? Nice. All right. Hope so. Again, this could hopefully be a nice way to start your finite element research. So Mahmoud says, do we need verification? What do you mean by verification? Like with experimental results? So do you need verification with experimental results? Not necessarily. So again, it goes back to one of those creative problems that we're looking at. If I were to do the tennis racket making contact with the strings, well, not a lot of experimental results out there. So for civil applications, yes, it's great, because if you guys can show that your model correlates very well with the experimental results, it strengthens your project. And it shows that the methodology that you guys used is correct. So it helps to have experimental results, but it's not required. Okay? Again, I want you guys to be creative. The whole goal of the finite element method is to get fun, have some fun with it. So don't worry about too much about verification. This is due April 16th. That's the last day of class. Sound good? Hopefully. All right, so that's the final project. Now, to inspire you guys, I threw out some sample projects. So if I go sample project 1, this was from Mohammed a couple years back. He's now graduated and a professor out east, and he did the numerical simulation of shear walls. So concrete shear walls. He actually did the testing of these too. So just the table of contents, table of figures, table of tables, and the abstract. So notice that the abstract isn't extremely long, right? Keep it short, sweet. That should be kind of the goal of the whole paper. Introduction, he shows his own testing. So this was actually conducted by the University of Toronto, but his walls were very similar. So he talks about the geometry of the walls, the reinforcement detailing, material properties, everything like that. Concrete, so if you guys are tackling concrete or masonry, any sort of cementous material, this is going to be very important to you guys, is this behavior under tension as well as under compression. As we can see, they're not similar at all, and it makes a big difference. Yeah, so you guys can just look through these. He shows his mesh, shows his reinforcement, how he modeled the reinforcement, his cyclic graphs. So if he was doing a report like this, question to the civil engineers, did Mohammed do a static? I better hide things. Would you guys do a static or a dynamic analysis if this was your case for these shear walls? Dynamic? Yes. So typically these are done with dynamic testing. These shear walls have a lot of inertial effects. That's how we start incorporating things like damping. Now, do you guys have to do a dynamic analysis? No. So I believe what Mohammed did was just a static pushover. As we can see, just that. That's fine. So the whole goal I want to show you guys with this is, even though a lot of our problems that we're dealing with in research and stuff is very complex, I don't expect you guys to solve the entire problem. I don't expect you guys to get the nice cyclic behavior curves. One of the things, as you guys are going to see in ABAQUS, is to actually get these curves, we need a lot of parameters. It's not just as simple as, here's the peak strength, there's my model. We have to deal with things like damage, stuff like that. It gets pretty messy. So that's the final project. Now, we're going to talk about the assignment, but we are going to do that after we're done the lecture, because the assignment is actually very nice. Or at least I think it's pretty nice. It's all, or I guess mostly ABAQUS based, this assignment. There's no real coding of the theory. All right, so if you guys didn't like coding, Mathematica, all that stuff, that's okay. We're done with that. We're moving on to ABAQUS. And there's a very specific reason why today that we're not going to code the theory. And I'm hoping that by the end of this, you guys are going to see what the problem is. Remember when I talked about the general outline of the course, I said that today we're going to see a big problem. And this is the problem that we are going to address next lecture. So let's get into the theory, and hopefully you guys can see what the problem is going to be when it comes to these elements. So lecture 5 here, we're dealing with something called solid elements. We looked at the picture, we said, oh, those are nice, those are pretty sexy. I want to learn how to use them. I want to learn the theory behind them. Well, today we're going to learn, and I'm going to warn you, it's actually fairly straightforward, but since they are complex, we're dealing with 2 and 3 dimensions now. It's going to get pretty ugly. So I'm just warning you now. So grab your snacks, grab your popcorn, anything you want, get comfy, and let's take a journey together. So the first thing that we are going to discuss is general solid elements. as you guys have seen from the pictures, when we see there was different types of elements. There's squares, there were triangles, and even though they're different types of elements, they're all still considered solid elements, and they follow the exact same mathematical formulations. So what we're going to do in this first part is we are going to introduce the mathematical formulations of a general solid element. So it could be 2 dimensions or 3 dimensions. And then what we're going to do after that is we are going to apply it to commonly seen elements. So those squares and triangles, those are actually called triangular and quadrilateral elements. Those are something we will be using quite often. So we're going to take what we learned in this first part here and then apply it to those specific elements. So we're going to start off, again, just the mathematical behavior of these solid elements. So until this point, we created elements for very unique scenarios, such as bars or trusses, or Euler-Bernoulli beams. How do we do this? Well, we basically use their differential equation. So right here we have a bar element. We took the differential equation of EA multiplied by the second derivative of the displacement function is equal to negative P. For the beams, we did EI multiplied by the fourth derivative of the displacement function is equal to Q. Right? We just took these differential equations, threw them into the Galerkin method, and we can derive their element formulation. Not too bad. But of course, as I was discussing, finite element method isn't just for us civil engineers that like beams and bars. It can be used for anything, and that's what we're going to get into today. But now, question for you guys. As civil engineers, or if you guys are mechanical engineers, feel free to answer. When would we use something like a bar element or a beam element? There is a very specific scenario where they come in handy quite a bit. What do you guys think? When would a bar or a truss element or a beam element be useful for a civil engineering application? Mahmoud on the money again. Reinforcement. So as you guys are going to see, when we start talking about solid elements, we're going to model the concrete as those solid elements. A beam of concrete, solid. But the steel reinforcement inside, which we just use for tension or compression, well, those could be modeled as a bar or truss element, or even a beam element if you guys are feeling fun. But yeah, so the stuff that we have learned, it is useful. It's just, it doesn't cover all the applications that we want. These solid elements that we're going to cover, well, they're going to cover basically any application that we want. It's going to be very beautiful. So let's look at this particular problem right here. If I were to give you guys this particular problem, and I were to say, all right, find me the stresses and the strains in that triangle. You guys will say, well, it's kind of a upside down beam, but then we have that lateral load, so we can't use the Euler-Bernoulli beam equation. It gets pretty difficult. Pretty difficult. So what we do is we can say, all right, well, even though this looks difficult, if I were to create it into a finite element problem, so I introduce some elements and some meshes, it's actually not that bad. We have 6 nodes. We know that we solve for nodal displacements. 3 of the nodes are actually fixed, so we only need to solve for 3 nodal displacements. Things are looking pretty good. And we said, all right, well, in order to do that, I need to know the stiffness of this structure. So the whole goal that we're going to try and figure out in this first lecture is what is going to be the stiffness of these solid elements. So this isn't a very particular solid element. It's just one of the cases, as we're going to see. But this is what we're trying to solve for. What is going to be the stiffness of these solid elements? If we had a beam and we knew the stiffness and we knew the applied loads, well, we can solve for those nodal forces. We're doing the exact same thing here. The only problem that we have right now is we don't know the stiffness. So when we're dealing with these 2-dimensional, or as we're going to see later, 3-dimensional elements, they get to be kind of a problem because they have 2 directions of motion. If I were to take this, my clicker, I can move it side to side, or I can move it up and down, which is something that we haven't seen before. For bar elements, we can only move it laterally. For beam elements, it would only go vertically. But now we're actually introducing something that can go 2 directions. And for 3D, 3 directions. So the question becomes, all right, what do I do? Well, remember that when we dealt with bars and we dealt with beams, we did an approximation function. And that approximation function was for its direction of motion. For the bars, our approximation function was laterally, and for beams, our approximation function was vertically. we're going to actually use the same procedure here. So what I'm going to do is I'm going to say that the motion of this element can be described as a vector with a component u in the horizontal direction and a component v in the vertical direction. And what I'm going to do is I'm going to have an approximation function for each one of those directions. So what I'm going to do is I'm going to take that vector, which is generalized just to u and v, and I'm going to approximate both of those directions. All right, so instead of u, I'm going to have my a naught plus a1 times x1 plus a2 times x2, and this is going to be the motion in the horizontal direction. And then I'm going to have a second component underneath it, and instead of a naught, a1, a2, I'm going to have b naught, b1, b2, etc. And this will be the motion in the vertical direction. So this is where things start getting a little bit complex, is because we're not just dealing with one direction of motion now, we have two. It's very simple though. All we did was we said, all right, well, I know approximation functions. I'm just going to have an approximation function for both directions. So that's all we did so far. Now let's start talking about the element degrees of freedom. Remember that when we were dealing with the finite element method, we didn't want to express things in terms of our approximation function. Remember that that approximation function is used for the entire element. What we really wanted, because this is how we solve for things using the finite element method, was to find the nodal displacements. So again, I didn't want the displacement in all of the elements. I just wanted the displacements at the nodes. So at those green points right there. So rather than having a general approximation for the entire element, what I'm going to do is I'm going to determine an approximation for the nodal displacements. So if I were to look at this, I can see that I have three nodes. So therefore at the first node, I would have displacements u1 and v1. At the second node, I'd have displacements u2 and v2. And then at the third node, I'd have displacements u3 and v3. Now, what we do is we actually use that approximation after we find those nodal displacements. So as you guys remember from the last assignment, when we dealt with the bar element, we first found those nodal displacements, so at each end of the element, and then from those nodal displacements, we used our approximation function to find the displacement within the element itself. But remember, we first start off with finding those nodal displacements. Well, same thing here. So we find those nodal displacements. So if I were to look at these nodal displacements, well, we know that our approximation function, just like the beam element before, can be a function of u1 times n1 plus u2 times n2, all the way on until un times nn. nn sounds a little funny. If I were to deal with this particular element with the three nodes, it would be u1 n1, u2 n2, and u3 n3. But of course, we're trying to figure out what this is for a general element. So it's going to go all the way on to un and n. So what we're going to do now is we are actually going to separate this vector into two vectors. Basically, what we're doing is we're going to take those nodal displacements, u1, u2, u3, v1, v2, v3, and we are going to separate them out from our shape functions. So all I did was I took that vector above and I separated out the shape functions from the element displacements. Because from here, I can create a nice vector describing my motion as simply the matrix n, which just consists of my shape functions, multiplied by a vector ue, which is those element displacements, or those nodal displacements, sorry. Now the question to you guys is, why did I do this? Why do you guys think I did this? What is the difference between n1, n2, n3, or etc., and u1, u2, u3? So what is the difference between the shape functions and the element or the nodal displacements? Anyone brave today? No? That's okay. You guys are just waking up. I'll give you guys the pass. So we got a message, nodal displacements are constant. Exactly correct. So when we look at our shape functions, we know that these are functions of x1 and x2. But when we look at our nodal displacements, they're constant. And that's going to be something very important moving forward. So now that I have this general displacement function, I can figure out what the strain vector is. As you guys remember from solid mechanics, if I know the displacement function, I can figure out what the strains are. So what we're going to do is we are going to look for the strain components in two dimensions. We're going to start off with the 2D case, and then we're going to move on to the 3D case. So again, our displacement function, it's simply this, n1, n2, n3, multiplied by some nodal vector, u1, v1, u2, v2, etc., etc. I'm going to say, all right, now that I know what this displacement function is, I can figure out what my strain vector is going to be. Now, in 2 dimensions, we have 3 components, epsilon 1, 1, epsilon 2, 2, and epsilon 1, 2. Now, what we actually know is that these terms can be calculated from our displacement vector. So our first term, epsilon 1, 1, well, that's the partial derivative of u with respect to x1. Our component epsilon 2, 2, this is the partial derivative of v with respect to x2. Now, you guys are saying, Clayton, hold on. What about epsilon 3, 3? What about epsilon 3, 1, etc.? Well, remember that this right now is just the 2D case. We're going to get into the 3D case, and trust me, it's messy. It's very, very messy. So what we're going to do is we are actually going to take the derivative of u and v. That's as simple as that. Now, if we look at our displacement function, again, we have a matrix full of our shape functions, and they're functions of x1 and x2. Therefore, we can actually take the derivative of those. But if we were to look at our element displacements, our nodal displacements, I don't know why I keep saying element displacements. Our nodal displacements, they're constant, so they don't really apply with the derivative at all. So for instance, if I was looking at that partial derivative, partially u with respect to x1, it's actually very simple. All I'm doing is I'm going down the row. My first component of u, well, that's n1. So I'm going to take the partial derivative of n1 with respect to x1. Go to the next entry, 0. Partial derivative of 0, well, that's going to be 0. Then the next entry, n2, well, the partial derivative of n2 with respect to x1, and I just basically do that for each one of the rows. So does it make sense where I got this big colorful matrix down below? What do you guys think? Is this matrix pretty clear on how it was obtained? Yes, perfect. So congratulations, this is all you guys really need to know for these solid elements, is this matrix right here. So what we're going to do is we're actually going to say that our strain vector is our matrix B, which is that big colorful matrix, multiplied by our elemental displacements. Now, question for you guys. What do you guys think this matrix B is called? Now, it's one of those things that it's actually called different things depending on where you look, but most call it the same thing. So what do you guys think that this B matrix is called? Compliance matrix? You guys are going to love this. So in most resources, because again, it changes depending on where you look, they just call it the B matrix. That's that engineering creativity at its finest. So this is simply going to be the B matrix. And this B matrix right here is all you guys will need to know. As you guys are going to see, our end formulations, the only thing that you guys, or if I were to show you guys the end formulations right now, every term in there will look familiar now that you guys know what this B matrix is. And we're going to go over so many examples that you guys will know exactly how this B matrix is calculated. All right, so now we're going to go into stresses, because again, if we now know strains, well, we can figure out stresses. There's a nice relationship between stresses and strains. So if we're dealing with the two-dimensional case, our stress vector is simply going to be sigma 1, 1, sigma 2, 2, and sigma 1, 2. And we said, all right, well, if I know the strains, we know that there's a relationship between those strains and those stresses. And what we do is we label that relationship between the stresses and the strains with that C matrix below. Now, those strains that we have, we already know what those are. So we're just going to call those epsilon right now. Now, if we were to look here and say, all right, well, I now know what those strains are, but that C matrix, I'm not really sure. Now, for you guys, another question for you guys. Do you guys know the C matrix there for a 2D problem? Remember, we're dealing with 2 dimensions. I remember in 3D, we have that nice 6x6 matrix, but we're not dealing with 3D. We're dealing with 2D. Do we have a C matrix for 2D? What do you guys think? Do we have that C matrix, that constitutive law for a 2-dimensional problem? Sabrina says yes. Let me give you guys a hint. So in 2 dimensions, all of the stresses or the strains will act in the same plane. Remember, it's a 2-dimensional plane. So now that I gave you guys that big hint, if everything acts in the same plane, what are you guys thinking of? Besides how boring this class is. Plane stress, exactly. So in 2 dimensions, everything's going to act in that same plane. Therefore, we can actually use our plane stress or plane strain constitutive laws. So just a reminder for plane stress, this is when sigma 33 is equal to 0. We have a nice 3-dimensional matrix for it. If I were to deal with plane strain, so when epsilon 33 is equal to 0, no problem. Again, I have a nice matrix for it. Inside of these matrices, well, there's 2 variables. E, the Young's modulus, which you guys know, and nu, the Poisson's ratio, which again, you guys will know. So now when we take another step back, we say, all right, well, we had that B matrix. It was crazy at first, but we now know what the B matrix is. The C matrix here, we now know. It's something that we actually covered before, so it's not even new. What can we do now? Well, as we're going to see, we're going to do something very beautiful. So we can wrap this up by saying that our stresses are equal to C times B times our nodal displacement vector, UE. So again, our strains were simply B times U, and our stresses are simply C times B times U. It's looking pretty good. Now, if I know my stresses and my strains, I hope that you guys are thinking, oh, virtual work. I know that you guys definitely weren't thinking that because let's be honest, no sane person thinks about virtual work. It's not very fun. But virtual work here is what's going to make everything very, very easy for us. So knowing our stresses and strains, we can apply the principle of virtual work. Those of you guys forgetting, the principle of virtual work is this big ugly equation that the internal virtual work is equal to the external virtual work. Now the key here though is when we're dealing with 2 dimensions and 3 dimensions, we're not dealing with an Euler-Bernoulli beam. We're not dealing with a bar. We're actually dealing with a continuum right now. So the formula that we are going to use was this big ugly one that we derived, where we have our internal virtual work on the left, and we have our external virtual work on the right. Now, our first component in the internal virtual work is our strains, or our virtual strains, since we're dealing with virtual work. Now, do we know our strain vector? What do you guys think? Do we know our strain vector? Reza says yes. Yes, we do. Remember, the strain vector was simply B times our nodal displacements. How about our stress vector? Do we know what our stress vector is? Yes. It's simply C, our constitutive law, times B times our nodal displacement vector. Therefore, I can substitute both of those in to get the following expression. Now, one thing that I really want to make clear is that when we look at our strains, we had virtual strains. And if we look at our stresses, we had the actual stresses. So therefore, when we're putting in this nodal vector, this nodal displacement vector, for the strain component, it's a virtual nodal displacement vector. And then for our stresses, since they're real, it's the actual nodal displacement vector. So I just want to make that very clear. Now what I'm going to do is I'm going to take this component, and right now I have my B, and I have my nodal displacements U, and I'm simply going to swap them. So I'm going to move them over to the other side, so now I get B transpose. Why is this nice? Well, if I look, my 2 constant things, my actual nodal displacements and my virtual nodal displacements, they're at the ends now of this big ugly matrix thing. Therefore, I can factor them out. So now I get UE star, which is our virtual nodal displacements, multiplied by the integral of B transpose times C times B, multiplied by our actual nodal displacements, is equal to our external virtual work. Now our external virtual work, it's looking pretty ugly right now. Let's address that. So remember that from before we have the following equation. Now this is kind of a problem because right now we have a general displacement field or virtual displacement field U star. Remember that in the finite element method, we're not dealing with the displacement field, we're dealing with the nodal displacements. But that's actually okay because we already determined what that displacement field is equal to. Remember, it's equal to our n, the n matrix multiplied by our nodal displacements. Therefore, we can replace this with this. It's nice and easy. Now, this is really nice because when we're dealing with our, now this is nice because we have our element, our nodal displacements. I'm going to get really confused saying that. I'm not too sure why. But again, when we look here, those I got to stop. Those nodal displacements, they're constant. Therefore, we can factor them out. Now, when you guys look at this equation, and I highlighted in red here to make it really obvious, what do you guys want to do with those virtual displacements? If I were to give you guys this equation, what would you guys do to this immediately? Cancel it out. Correct. Very correct. So since it's in front of every term, we are simply going to cancel it out. And we are left with this final equation right here. And this is our end equation. No more simplification. So do you guys know why this equation looks so familiar almost? I guess it probably doesn't look familiar, but if we were to take a step back, this equation has the following form, where we have a matrix K multiplied by our displacements is going to be equal to our forces. This is exactly the same form that we had back for our bar element. Now we just solved it for a continuum. So if we were to say, all right, well, I want to actually make this look a little bit prettier, Clayton, give me the exact equations. Well, we said that our equation after the virtual work is equal to this, and we know that it has the following form. Therefore, this is going to be our stiffness matrix, simply the integral over the element, a B transpose multiplied by C multiplied by B, and then our nodal forces vector on the other side is simply going to be an integral of two things. The first one is going to be our traction vectors, and the second one is going to be our body forces. And we're going to talk more about those later. So if you guys are a little bit confused, don't worry. I know that we've spent so much time on beams that it may be a little bit confusing, but don't worry. However, what we can conclude right now is that our stiffness matrix K, we have a nice discrete equation for it. It's simply the integral over the length, or not over the length, dealing with beams too long. It's simply the integral over the element of B transpose multiplied by C multiplied by B. Now C, that constitutive law, we've already figured out what that is a long time ago. That was back in the constitutive relationships. So the only unknown that we actually have here is that B matrix. But now you guys have seen that B matrix. So nothing in this formula is actually unknown or anything crazy. Now, what might be a little bit more foreign is that nodal forces vector on the other side. But again, if we look at it, it's composed of basically three things. One is that matrix N, but remember that that was just our shape functions. That was nothing too special. If you guys go back to the beginning, all we saw that it was N1, 0, N2, 0, N3, 0, etc. And then the second row was 0, N1, 0, N2, etc. So it's actually really nice and easy. Our traction vector, you guys are saying, well, Clayton, what is a traction vector? Well, this would be the equivalent of a 2D distributed load. All right, so 2D distributed load. Remember in beams when we had those distributed loads? This is the 2D equivalent. And then finally, our body forces vector, which is simply things like gravity, something that takes a mass and moves it, depending on which direction. So from here, we can conclude some general things. Both of these are going to be needed to determine our nodal displacements. It makes sense. It's just like the bar element before. We had to figure out what the stiffness is, we had to figure out what our nodal forces are, and then from there we can figure out what our nodal displacements are. Well, it's going to be the same thing here. And we're doing the exact same thing. We're going to find that stiffness, find those nodal forces, solve for the nodal displacements. There is one problem, or one thing that we haven't defined yet. If we were to look at those two vectors, the only two things that we don't know from straight theory or external loads is going to be the n vector, our shape function vector, and the B matrix. Or I guess the n matrix and the B matrix. Now the B matrix is a function of the shape functions. The n matrix is a function of the shape functions. So my question, have we covered the shape functions for these elements yet? No, we have not. And that's what we're going to do in the later part of the lecture. Is as we're going to see, depending on what element we select, a triangle, a square, they'll have different shape functions. But no matter what element we select, that equation that we have there, it's always going to be the exact same. So all we need to do is we're going to take our element, find the shape functions. From there, we just substitute everything into this equation. We are good to go. So again, we don't have the shape functions, which are needed for b as well as n. Now, these shape functions are going to depend on two things. One is element type. So this would be if I'm using a triangle or a square, something like that, as well as the geometric order. So remember, for bar elements, we had two. We had a linear and a quadratic, and the same thing is going to happen here. So this is for the two-dimensional case, right? We did everything in 2D. Now you're saying, Clayton, who cares about 2D? I want 3D. Well, of course. So let's look into 3D. So now that we have the stiffness matrix and the nodal forces vector for a 2D case, how about 3D? Well, let's look at our potato. We know that our potato can be modeled using these brick elements with nodes. There's only two major differences that we're going to see. One is that when we look at a 3D element compared to a 2D element, does it typically have more nodes or less nodes? 2D versus 3D. What's going to have more nodes? "3D, yeah. So as we can see here, we went from 4 nodes before, or I guess we dealt with the triangle, so we went from 3 nodes, now we have 8 nodes. So we have more nodes, but as we've seen when we're coding things, nodes aren't really a problem. We just have to make our loop a little bit bigger. The other problem with 3D, or the only thing that makes 3D a little bit more complex, is the fact that we add that third direction. In 2 dimensions, we had u and v, so we had horizontal and vertical, but in 3D, we have that third direction into the page, so we have to account for that. But the same process applies. We say that, all right, well, this element right here has 3 directions of motion, but I don't care about the general directions of motion. What I care about are those nodal displacements. So each one of these nodes simply has an additional nodal displacement, that being the w direction. But the same thing occurs as in the 2D case, where I can express my displacement field. Instead of a vector uv, I have a vector uvw. But the same thing happens. I'm going to approximate each one of these directions as follows. So I have my a0 plus a1 times x1 plus a2 times x2, etc. But then I say, well, I don't really care about those general displacement functions right now. I want everything in terms of the nodal displacements. So I get u1 times n1, u2 times n2 plus ... un times nn. And then all I'm doing is I'm adding that third component to the bottom. So w1 times n1, w2 times n2, etc., etc. But things do get a little bit more messy, because now that I have this, we have something else. And as you guys are going to see, it's not too fun. But we're going to do the same process as before. We're going to separate the shape functions from our nodal displacements. So this is where things start getting a little bit different than 2D, but it's still the exact same. It just looks more complex. So when we separate it out, in 2 dimensions, our n matrix right there, it had 2 rows, one for both of the directions, u and v. Now we have 3 rows, but the formulation of the n matrix is still the same. It's just n, 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 n2, 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 n3, 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 etc. The only difference is we now have that third row. But just like before, we can express this as simply n multiplied by our nodal displacements ue. So notice how this is the exact same expression as before. The only thing that has changed for us is our n matrix. That's the only thing that's changed so far. We simply have that third row. Now, question for you guys really quick. That having that third row, of course, makes things a bit more complicated. But what is going to make this much more complicated when we're dealing with 3D? Let's see if you guys... There's 2 things that change in 3D. The first is n here, and the second one's going to be something else. What else is going to change in 3D? What matrix? The B matrix. So Sabrina's right on the money. And it's going to get ugly. Gonna get really ugly, so buckle up, guys. So when we're dealing with stresses and strains, we're saying, all right, no problem. Again, exact same procedure as 2D. If we were to look at our strain components, same procedure. I have my strains, but this time it's not just 3 components. It's 6 components. Epsilon 1, 1, epsilon 2, 2, epsilon 3, 3, and then epsilon 1, 2, epsilon 1, 3, and epsilon 2, 3. And you're saying, Clayton, this is gross. Well, yes, and it's going to get even more gross. So we can actually figure out what these are equal to. Again, this just comes directly from the strain tensor. And if we were to substitute everything in, we get the following. So now if we look, well, it's the same form as before where we have a B matrix multiplied by our nodal displacements. The only difference is that B matrix looks like complete garbage now. But this is the only difference in 3D. We have a different N and we have a different B. And that's going to be the exact same thing. And I know what you guys are thinking. This is absolutely gross. Yes, very gross. If we were to look at this and do this by hand, it's terrible. No one wants to do that by hand. But that's why, as you guys will see, the finite element method, it's suited for computers, which is perfect for us. So those are the strains. Well, how about the stresses? Well, we know that we're going to have 6 stress components, just like strains. But again, it's going to be the exact same thing as before, where we can relate those stresses to the strains using a constitutive law defined by the matrix C. And say, all right, well, I know that the stresses are simply B times U. Therefore, our strains are B times U. Therefore, our stresses are simply going to be C times B times U. And if you guys are saying, hold on, Clayton, well, what is C now? Because we can't use plane stress or plane strain. We deal with 3 dimensions. Well, for a linear elastic isotropic material, we actually have a very nice C matrix. Well, it's not very nice, but of course you guys can code it, and the computer does all the work. But if we look here, nothing too crazy. If we were to go back to the principles of virtual work, now that we know the stresses and the strains, we can go to the exact same equation where our internal virtual work is equal to our external. And then we say, all right, well, we're still dealing with a continuum. The only difference is it's now a 3D continuum. We can see that all the components in here are going to be the exact same as the 2D case. Therefore, we derive the exact same equation. Therefore, we have the exact same stiffness matrix and the exact same nodal forces vector. So in general, the process is the exact same as the 2-dimensional case. The only difference is now our N matrix, our shape function matrix, it has that additional row because we have that additional direction. Our B matrix is also much grosser because instead of 3 strain components, we have 6 strain components. But that's it. So again, when we look at these equations, exact same equations, the only difference is going to be our B as well as our N matrix. But we have the same problem as before. Even though these are the exact same equations we can theoretically solve, well, we're still missing those shape functions. So we're going to discuss those here real soon. But before we do that, we're going to talk about something called general element requirements. So when we're dealing with the finite element method, we don't typically have one element. We typically have multiple. As you guys remember from your assignments, you guys had 4 elements, then you guys went to 2 elements. The key here is there's typically more than one element. So we have to define some rules between them to make sure that they behave pretty well. The first one is isotropy, which means that it does not favor one direction over the other. I'm saying, Clayton, I don't understand what that means. Well, neither did I. The best way to show it is an example. If I were to use the following approximation function, where I have a naught plus a1 times x1 plus a2 times x2 squared. Well, of course, it can be seen that the change in the x2 direction is going to be greater than x1 because we have that squared component. Now, when we talk about these general element requirements, these are general requirements. They're not always necessary. As you guys will see in this course, if you guys are dealing with mechanical or structural, 99% of the time you guys will follow these requirements. They're not required, but for a good element, you guys need to have these. So the second one is the ability to model rigid body motion and constant strains. If I were to look at this approximation right here, what's the problem with it? What do you guys think? If I were to use the following approximation function. No? That's okay. There's no A naught term. Therefore, the displacement actually changes along the element because every term there has or is a function of x, whether it be x1 or x2. Therefore, this right here could not model rigid body motion. Remember, rigid body motion is where every point displaces the exact same. But as we can see from this equation, every point does not do that because it's always a function of x1 or x2. And then the third one, and this is where it gets a little bit tricky, is element compatibility. St. Clayton, what do you mean by that? Well, I'll show you what I mean. When we dealt with our bar element back in the last assignment, we found the displacement function was something like this, right? Element compatibility ensures that this approximation that we now have is continuous. So when we look at when we changed from element 1 to element 2 in the center there, they still had the exact same value of displacement at that node. We didn't have a jump or a gap. Now, if we were to look at the stresses that we did afterwards, we found something like this. Now, as we can see, there is now that jump, okay? That jump in the stresses is fine, but if we had that jump in the displacement, it's actually not so fine. So what we want is we want our general elements to be something what we call C0 continuous, which means that our displacement field is going to be continuous, as we see it is, but all the derivatives afterwards, they don't have to be continuous. Okay? So again, our displacement field is continuous, but everything after the displacement field doesn't have to be continuous. Are you showing? Yes. So those two equations for the isotropy and the rigid body motion, those are two approximation functions that don't satisfy the requirements. Sorry, I should have cleared that up. Thank you for pointing that out, Nathan. Those two displacements do not satisfy general element requirements. It's easier to show you guys what doesn't satisfy than what does satisfy. So now, when we're dealing with these continuous things, when we're dealing with something called C0, everything will always be C, but that number afterwards, in this case 0, what that number represents is the number of derivatives you guys can take afterwards that'll still be continuous. So since our first derivative here, which is strain, which is then related to stresses, is not continuous, we say that this is C0. If I were to say something is C1, it means that the first derivative of our displacement will still be continuous. Now, question for you guys in the chat. Can you guys name me an example of something that would be C1 continuous, where its displacement as well as its first derivative will have to be continuous? What are you guys saying? This is a hard question. It's a really hard question. Something that we know that its displacement as well as its first derivative needs to be continuous. So something that's what we call C1 continuous. That's a hard question. So the answer would be a beam element. What is the first derivative of a beam element? Strain? No, not for a beam. If we're dealing with a beam, and I gave you guys the displacement function of a beam, and I were to ask for the first derivative. Angle? Yes, so it's the slope. And that slope has to be continuous over the beam. So the beams are what we call C1 continuous. Now the elements that we're going to discuss here real quick, they're all going to be C0 continuous. Now C0 continuous, even though it sounds like it's weaker, it's actually beautiful. And the reason why is this, is if I have an element and it is C0 continuous, I can figure out everything about that element just from the two nodal displacements. So remember that when we first solved in the assignment for our beam element, we just found the nodal displacements, U1 and U2. From those nodal displacements, I was able to find the displacement in the element, the strain in the element, and the stresses in the element, just from two nodal displacements. If it was C1 continuous, well, that's not quite the case. The elements start talking to each other in C1 continuous. So even though I know the two nodal displacements, the element over on the other side is still going to impact what happens on this element. So even though C1 sounds more beautiful, more powerful, C0, we're going to love it. So again, all we're requiring is that the displacement is continuous, and everything else, all the derivatives afterwards, they don't have to be continuous. And that's it. So now we're going to discuss triangular elements, but I'm sure that you guys can use a break. I know I can at least. So how about we take a 5-minute break, then we're going to come back and discuss triangular elements. So again, we found the stiffness matrix, we found our nodal forces vector, but we didn't define the shape functions. So now we're going to actually look at specific elements and define their shape functions. All right, so how about we take a 5-minute break, and I will see you guys back at 9:10. Sound good? Alrighty. Well, it's 9:10, so let's begin. So remember that we said that we now have the formula for our nodal forces vector and our stiffness matrix, which is the only thing that we need when we're solving for our nodal displacements. The only problem is to calculate that nodal forces vector as well as that stiffness matrix, we needed the shape functions, right? We needed those shape functions, and we didn't have them. And now I said that those shape functions actually depend on two things. The first one is what element type that we want, and the second one is the geometric order of that element type. So for example, this would be, am I choosing a triangular or a quadrilateral element? And am I choosing a linear or a quadratic element? And we're going to discuss all of those in this next lecture. So we're going to start off with triangular elements. These are kind of the fun ones. So triangular solid, oh, I need to click here. There we go. So triangular solid elements. So again, now that we have that stiffness matrix and nodal forces vector, let's look at the most commonly used element types. So again, we had our stiffness matrix as the integral over the element of B transpose C multiplied by B. And then we had our nodal forces vector, which is just basically the traction vector and our body forces. And we said, all right, well, this is great because with those two things, if I have my stiffness and I have my nodal forces, I can calculate my nodal displacements. But both of these have either a B matrix or an N matrix, which we need the shape functions to actually figure out. And we said that these depend on the element type and geometric order. So let's start our little journey through the elements with triangular elements. And we're going to examine two. The first is the linear triangular element. So it has 3 nodes, one at each corner of the triangle. And we have a second one, which is a quadratic triangular element. So same shape, it still has those nodes at the corners, but we introduce an additional node in between each of the previous nodes. So this one has a total of 6 nodes. Now, question for you guys. That quadratic triangular element, that picture there, how many elements is that? Is that 1 element? Is it 3 elements, 4 elements, 5 elements? How many elements? How many elements are in that quadratic triangular element picture? 1, exactly. And that's one of the things I really want to emphasize. Again, if you guys have taken 660, structural analysis, everyone's used to having one node at each element, which caused a lot of problems in the assignment, because when we dealt with the quadratic element in the assignment, a lot of people thought that there was actually 2 elements there when it was just 1 element with 3 nodes. So we have to get used to the concept that a single element contains as many nodes as you want. Now, is there such thing as a cubic triangular element? Well, yes, there is. Instead of 1 element between each of the nodes, or sorry, 1 node between each of the old nodes, we have 2. Now, will you guys ever use a quadratic triangular element? Well, no. The reason why I'm only covering linear and quadratic is because with these two, you guys can easily get good results. And when we start looking at things like ABAQUS, ANSYS, they only have linear and quadratic. They won't go to cubic because it's not necessary. As we're going to see, once we get into quadratic, the formulations are going to get pretty gross. But before we do that, let's look at the linear triangular element. Now, this element is also referred to as the CST element, or the constant strain triangle. And you guys are going to see why. So, to begin, we said that we have our element here. And for a linear triangular element, we have one node at each of the corners. So we have a total of 3 nodes. Now when we define nodes, or how we number nodes in finite element programs, is we start at the bottom left corner and we work our way counterclockwise around. So we're going to go 1, 2, 3. All right, 1, 2, 3. Nice and easy. So we have 3 nodes, 1, 2, 3. And for our calculations, we're going to say that each of those sides is 1 unit long. Okay, 1 unit long. You guys saying, hold on, Clayton. Will they always be 1 unit long? What do you guys think? Are these elements always going to be 1 unit by 1 unit? What do you guys think? Depending on the mesh, so that's basically, no, they won't always be 1 unit. And that's correct. So Mahmoud, you're on a roll today. These elements can be, let's say, 3 units long by 7 units long. The reason why we're just assuming 1 unit will become apparent later on, as you guys will see. So if we are doing a linear triangular element, well, of course, we're going to use a linear approximation function. Now again, this element has 2 directions it can move. It can move left or right, or it can move up or down. So my approximation function for this one is going to be a 2D vector, u and v, and again, both of these are going to be just linear. So we're going to have a0 plus a1 times x1 plus a2 times x2 for the u direction, and we're going to have b0 plus b1 times x1 plus b2 times x2 in the v direction. But again, we said in the finite element program, we don't care about the general displacement field. What we're really after at the beginning is the nodal displacements. So what we're going to do is we're going to take our current displacement function, and we are now going to express it in terms of the nodal displacements. So if we look here at element 1, we know that it has nodal displacements u1 and v1. If we look at element 2, nodal displacements u1, v2, and the same for node 3. So each node here in this case has 2 degrees of freedom. So before that, they only had 1 degree of freedom. When we looked at bars, the only degree of freedom was in the u direction. When we looked at beams, the only degree of freedom was in the vertical direction. But now each one of these nodes has 2 degrees of freedom, 1 for each one of the directions. But that's fine because we have a displacement vector that accounts for that. So our displacement function is simply u1 times n1 plus u2 times n2 plus u3 times n3. As we're going to see, the number of n terms is going to be directly proportional to the number of nodes that we have. All right, so since we have 3 nodes, we have n1, n2, and 3 in both of the vectors. So now the question is, all right, now that I have my displacement function, what is my shape function? Well, we're actually going to use the exact same process that we did for 1D elements. So what I'm going to do is I'm going to have my element here, and for shape functions, they have a very particular thing in that we have 3 shape functions, 1 for each one of the nodes. Now, at the node that we're interested in, so at node 1, we're dealing with n1, the shape function has to have a value of 1 at that node. So if I'm looking at n1 and I'm looking at node 1, it has to have a value of 1. Now for the other 2 nodes, nodes 2 and 3, it has to have a value of 0. So our shape function has to look something like this, where it has a value of 1 at node 1, and has a value of 0 at nodes 2 and 3. Sorry, I got to drink some water. Now for this particular case, our shape function is going to be 1 minus x1 minus x2. And it's very easy to show this in Mathematica. A little bit later on, when we get to a more complex example, if you guys don't know where these shape functions come from, I will show you guys in Mathematica. It's the exact same process that we did before. If I were to look at n2, so now I'm looking at node 2, well, we know that our shape function has to have a value of 1 at n2 and a value of 0 at the other 2 nodes. So it has to be something like this. Well, for this case, our shape function is simply just going to be x1. And finally, for our third node, again, our shape function has to have a value of 1 at the third node and a value of 0 at the other 2 nodes. So it's going to look something like this, and our shape function is just simply going to be x2. Now that we know our 3 shape functions, the rest is easy, because we said that's the only part that was missing. So the first thing that we said that we use our shape functions for is our n matrix, our shape function matrix. And for 3 nodes, it's simply going to be n1, 0, n2, 0, n3, 0. And then the second row, 0, n1, 0, n2, 0, n3. So do you guys see a pattern on how this n matrix is depending on the nodes that we have. It's pretty simple. Now, I'm going to leave that question for a little bit later because we're going to discuss other ones. And as you guys will see, our N matrix is going to be basically the exact same for all of them. But now we know what N1, N2, and N3 are. Therefore, our N matrix is simply going to be 1 minus x1 minus x2, 0, x1, 0, x2, 0. And the same thing below, just offset by one of the columns. And we're saying, Clayton, this is great. Because now that I also know the shape functions, I can figure out what that B matrix is. So remember, for 3 nodes, our B matrix is going to be something like this. Therefore, we can say, all right, well, what is the partial derivative of N1? What do you guys say? If I wanted the partial derivative of N1, which is 1 minus x1 minus x2, what's the partial derivative of N1 going to be? With respect to x1. Yes, negative 1. How about the partial derivative of N1 with respect to x2? Negative 1, yes, on the money. So what we do is we basically just repeat this process for all of those terms now that I know what N1, N2, and N3 are, and I get this right here. So this is my B matrix for a constant strain triangle. And this is where the name comes from. Because as we can see here, this B matrix, it's constant. And remember what the B matrix is. It is basically the relationship between the strains and the nodal displacements. So my nodal displacements, those are always going to be constant. Always. They're just the displacements at the nodes. So if our nodal displacements are constant and our B matrix is constant, well then our strains are going to be constant. So this is why it's called the constant strain triangle. All of our strains are actually going to be constant. Now that we know our B matrix, we can go on to our stiffness matrix. Well, how do we calculate that? Well, we derived a nice formula in the previous little lecture topic, which was the integral over the length of the element of B transpose times C times B. From the previous slide, we now know exactly what B is. Do we know what C is? Well, it depends. Are we assuming plane stress or plane strain? As you guys are going to see in ABAQUS, once we define our elements, and if we're dealing with a two-dimensional case, we actually need to specify, is it plane stress or is it plane strain? So what I'm going to do for the purposes of illustration is I'm going to assume plane strain. Another thing I'm going to do, and this is also done in ABAQUS, is when we're dealing with 2D elements, the thickness into the page or into the screen, that's considered constant. So what I'm going to do is I'm going to call that thickness T, and that means I can bring it outside of the integral. So as you guys can see over on the other side here, we bring the T out because if we're integrating over the element, it's a triple integral. But what happens is since I said that in-plane thickness is constant, I can have T. Now the reason why I put the units of that element from 1 to 1 is so that I can define some integration limits. All right, that's the only reason why I did it. I did some integration limits. Now, since we're dealing with the triangle, we have to modify our integration limit on one of them because it's sloped. It's not just a nice square. But if we were to look at the terms in here, well, this is simply B transpose. This is simply C for plane strain, of course. If it was plane stress, it'd be a little bit different. But this is going to be B. So all we're going to do is we're going to mush that all together and then integrate it twice. And this results in a 6x6 matrix. A 6x6 matrix. And this makes sense because we have 3 nodes, and each node has 2 degrees of freedom. 3 times 2, going to be 6. Nice and easy. Now, I'm going to ask you guys, remember I said that there's a big problem that we're going to have when we deal with these elements. If I were to give you guys this right now, and I were to ask you guys to do it using a calculator, okay, a calculator. What don't you like about this? What sucks? What are you guys thinking? Clayton, I don't like it. The integrals. That's exactly correct. This is one of the nicer integrals. As we're going to see, finding the stiffnesses of these elements is going to be a pain in the ass because of those integrals. And we're going to discuss more about that a little bit later. So now we're going to go on to the nodal forces. So of course, if we know B, we can also determine the nodal forces due to 2 different things. The first one is body forces. This would be something like gravity. And the second one is traction vectors. So this would be like a distributed load. So for body forces, we know it's the integral over the elements of n transpose times rho b. Well, same thing as before, we're going to assume a constant thickness t into the page, and we can simplify it into the following. Our n transpose, that's just our shape functions. b1 and b2, think of that as the gravity in the horizontal direction, which in reality is going to be 0, and then the gravity in the vertical direction, which we know is negative 9.81 meters per second squared. So this is actually nice and easy. The only thing that you guys have to remember for these body forces is we're integrating over the volume. So after we take out that thickness t, we're still left with a double integral. Now you guys may be saying, Clayton, what exactly does this formula do? And this is my fault. I didn't really show you guys it too much in the bar element. Well, this is what happens. Our element we know is subjected to something, let's say gravity. Okay? So we know that over the volume of the element, it wants to move downwards because of gravity, and it depends on the size of the element, etc. But those forces right there, we can't account for them. Remember that when we're solving our system, we're solving for nodal displacements based on nodal forces. So what this equation does is it actually takes those gravity forces that are applied throughout the element and converts them to equivalent loads at each one of the nodes. So that's why we're doing this, is because, again, all of our forces need to be at the nodes. They can't be throughout the middle of the element. So all we're doing is we're taking our loads that would be in the elements, and we're simply creating equivalent loads at the nodes. So how about traction vectors? Well, it's the exact same formula. The only difference is instead of rho b, we have Tn. Another thing that we have to consider too when we have our traction vector is that these are over the surfaces. So instead of 2 integrals, I just have 1. Now in this case, I picked this surface right here, that left surface. So I'd be integrating from 0 to 1 with respect to x2. But just like before, what exactly are we doing here? Well, we're taking this distributed load that's going across our element, and we're converting it to an equivalent nodal load. Because again, when we're solving the system, we're only looking at nodal displacements and nodal forces. All right, hopefully that makes sense to you guys. So now let's move on to the big bad boy, the quadratic triangular elements. Now, as you guys may picture, it's pretty ugly. The reason why, it has 6 nodes. 6 nodes. As you guys are going to see, when we start increasing the nodes, things get a lot uglier. Now we're dealing with quadratic elements. Nathan says, did we ever resolve how to do the integrals? The integrals can be taken as they are. If you guys were to go into Mathematica and put one of those integrals in, it's fine. It will solve it. The only problem is, and we're going to discuss more about this next lecture, is that integral right there, or specifically if I were to go all the way back. This integral right here, you guys can solve that in Mathematica. The problem with that integral right there is it's going to take forever. And that's just for one element. So what we're going to do later on is we're going to figure out a way how to solve these much easier. But this integral, it's completely fine. If you guys wanted the stiffness of the matrix, or sorry, the stiffness of the element, and you guys were to plug exactly that in, good to go. No problem at all. So this can be solved. It's just pain in the ass to solve. Of course, in this class, use Mathematica. Please don't solve an integral by hand. All right, so we're going to go back into the the quadratic elements. So now we have 6 nodes. 6 nodes. So the way that we define quadratic elements, or how we number the nodes in quadratic elements, is a little bit different. First of all, we label the linear elemental nodes. So we go 1, 2, and 3 at the corners, and then we make another pass and label all the middle nodes. So you see how we go 1, 2, 3, and then we could do another pass, 4, 5, and 6. Okay? 4, 5, and 6. The reason why we have such a specific numbering scheme is because, of course, we throw all these into computers. When we throw them into computers, we need to make sure we know the locations of each one of those nodes. Now, if I'm dealing with a quadratic triangular element, of course, I'm going to use a quadratic approximation function. So instead of A0, A1, x1, A2, x2, I now tack on an A3, x1, x2, plus A4, x1 squared, plus A5, x2 squared. So this is where the complexity starts happening, is my approximation function just got a lot grosser. Just like before, though, I don't care about the approximation function yet. What I'm interested in at the beginning are the nodal displacements. Now, since we have 6 nodes, there's a lot more nodal displacements to keep track of. Instead of U1, U2, U3, I now have U1, U2, U3, U4, U5, and U6. And the same thing for the vertical direction, V1, V2, V3, V4, V5, and V6. Well, even though it looks pretty bad, we can still keep it in terms of a nice displacement function as U1 times N1 plus U2 times N2 plus U3 times N3 plus U4 times N4, etc. So another thing that we realized is by adding those additional nodes, we created 3 additional shape functions. Before we had 3 shape functions. Now we have 6. So let's talk about what those are. Again, we can use the exact same process as a 1D element, and this time it gets a little bit more gross. Because remember, the shape functions have to satisfy the same criteria as before. You're saying, Clayton, what does this mean? Well, if I were to look at node 1, our shape function n1 must have a value of 1 at node 1 and a value of 0 at every one of the nodes. So it's going to look something like this. Where again, at node 1, it has a value of 1, and at all the other nodes, it has a value of 0. Well, this means that my shape function n1 is going to be 1 minus x1 minus x2 multiplied by 1 minus 2x1 minus 2x2. You're saying, Clayton, what about the other 5 shape functions? Well, here they are. As we can see, things are getting pretty gross. And things are going to get really messy. Do you guys know why they're going to get messy? What's the major difference between these shape functions and the other shape functions that's going to cause, not problems for us, because again, we're just throwing everything in Mathematica, but what's going to make Mathematica sweat? What do you guys think now is the complexity that we just added? x1 and x2 in a single term. That's true. That's true. And building upon that, it is this. The derivatives of those shape functions, because remember, the B matrix is basically just a bunch of derivatives of our shape functions. That's no longer constant. They're going to be functions of x1, x2. So if I were to write out my N matrix, it's going to be the exact same as before. The only difference is I have to add in the N4, N5, and N6. But when we, which is a problem because I'm running out of colors. But when we get to the shape functions, this is where things get really messy. Actually, the B matrix, because again, we're taking the partial derivatives of each one of those shape functions, and they're not just constant values anymore. Am I going to solve it for you guys? No. It's too gross. It's too gross. So now that we have N and B defined, even though I didn't show you guys what it is, you guys can look in Mathematica if you guys want, well, then we can theoretically calculate our stiffness matrix, which depends on plane strain or plane stress. And this will be a 12 by 12 matrix. Again, easy to see because we have 6 nodes. Each node has 2 degrees of freedom. Therefore, we have 12 total components. Our nodal forces, same thing. The only difference is, of course, that N matrix, it just got a whole lot longer. But this results in a 12 component vector. Now, as we're going to see, the complexity of the calculations is directly proportional to the degrees of freedom of the element. What does this mean? Well, once I get into 3 dimensions and I add that third direction, things are going to get a lot more gross. A lot more gross. All right, so this was a 2D element. That 12 by 12 matrix, that was for one element in 2 dimensions. Imagine 3D. Well, of course, we know that there are 3D elements. Now, the 3D version of a triangular element is called a tetrahedron element. Now, a linear tetrahedron element has the following form. It has 4 nodes, and it has 3 degrees of freedom at each one of the nodes. So question for you guys, what would the stiffness matrix size be for this element? 6 by 6, 8 by 8, 12 by 12, 16 by 16? What do you guys think? 12 by 12? Correct. And this is probably the most simplistic 3D element. Now, of course, just like the triangular elements, there's also a quadratic version where we add additional nodes at the midspan of each of the old nodes. This one now has 10 nodes and 3 degrees of freedom. So, of course, the stiffness matrix for this one is going to be 30 by 30. And again, this is just one element. Typical finite element models have 10,000 elements. 10,000 elements and each element has a 30 by 30 matrix. You're looking at some gross computation time. Now, even though I'm not showing you guys these, the process in finding them is the exact same. We find the shape functions, we find the B matrix from the shape functions, and we find the stiffness matrix. So that's it for triangular elements. Is there any questions about those before we get into quadrilateral elements? Are you guys feeling pretty good? Hopefully feeling pretty good. All right, I'm going to take it you guys are feeling pretty good. So now we're going to talk about quadrilateral solid elements. Oh, good question. So Mahmoud asks, is it mandatory to be a right triangle? No, it is not. As we're going to see, it doesn't matter. If we were to do this and I were to ask you guys to use this method, of course it will matter, because if it's a right triangle or if it's not a right triangle, it'll change your integration, basically. Remember that we're integrating over the element. So if our element's really wonky looking, it's going to have a different integration scheme. It's still a double integral, but we have to modify our limits. But as we're going to see, we're going to introduce something next lecture that it doesn't matter what our element looks like. And I was actually going to talk about that towards the end, but that's a great question. It doesn't have to be a right triangle. For our calculations, we made it a right triangle. But again, the only thing that you guys would modify are going to be those integration limits. So now that we have a oh, sorry, did that answer your question, Mahmoud? Hopefully. Yes, perfect, perfect. As we're going to see, we're going to do something very, very beautiful next lecture. So be ready. So again, we're going to do the exact same thing. And as we're going to see, there's going to be these slides were actually copy and pasted. I just changed them from triangular to quadrilateral because the process for all these solid elements is going to be the exact same. So once you know it for one, you basically know it for everything else. So again, we have our stiffness matrix, B transpose C times B, then integrated over the element. And we have our nodal forces vector. And we said that, well, the only thing that we're missing is B and N, which are both functions of the shape functions. So all we're going to do for the quadrilateral elements is figure out what the new shape functions are. So we're going to look at two types of quadrilateral elements. And if you guys are modeling anything, these are probably what you guys will actually be using. The first one is going to be a linear quadrilateral element. So it has the nodes at each one of the corners. And the second one, 4 nodes total. And the second one is the quadrilateral or quadratic quadrilateral element. That is a tongue twister right there. Now this one has 8 nodes, and they're basically at each corner of the element and then 1 at each of the midspan. Now these are going to get very messy, so I hope you guys are ready. So let's start with the linear quadrilateral element. As we said, it has 1 node at each of the corners. Now, kind of following up to Mahmoud's question, does this element need to be a perfect rectangle or a perfect square? No, it doesn't. It could be a trapezoid. It's still quadrilateral because it has those 4 nodes at each one of the corners. Okay, so I just want to really emphasize it. So the triangle doesn't have to be a right triangle. These don't have to be perfect squares. They could be anything. The only reason why we're keeping them as right triangles and perfect squares right now is to keep our integration as simple as possible. All right, so we have 4 nodes, and just like before, we start at the bottom left and we go counterclockwise. So we go 1, 2, 3, and 4. Now, if it's a quad, and we're going to say that the bottom length is 2a and the top length is 2b. Now, since this is a linear quadrilateral element, of course, we're going to do a linear approximation function. So we're going to have a0 plus a1 times x1 plus a2 times x2 plus a3 times x1 times x2. So as we see, it's almost the exact same as the triangular element, except we have a3 times x1 times x2. And the reason why we're allowed to add that additional term, well, that's because we have an additional node. The number of a coefficients that you guys have is directly proportional to the number of nodes that they have. So in this case, since we have 4 nodes, we're allowed 4 a coefficients. But just like before, we don't want that approximation in terms of the general displacement function. We want it in terms of the nodal displacements and the shape functions. So if we're dealing with a 2D case, we know that each one of these nodes has 2 degrees of freedom. Therefore, we have U1, U2, U3, U4, and then V1, V2, V3, V4. Therefore, our approximation function is now U1 times N1, U2 times N2, U3 times N3, U4 times N4. As you guys can see, it's starting to get a little bit more messy. We're saying, all right, Clayton, well, how about the shape functions? Again, Same process as before. So if I were to take this element and I were to look for n1, well, we know that n1 must have a value of 1 at node 1, and then the value must be 0 at nodes 3, 4, and 5. Sorry, nodes 2, 3, and 4. There is no node 5. Don't worry about node 5. Now, if I were to satisfy this, I simply get b minus x2 multiplied by a minus x1 divided by 4ab. I say, all right, well, that's not too bad. How about the next one? Well, if I'm looking at the shape function n2, this must have a value of 1 at node 2 and a value of 0 at the other nodes. Well, the function for this is going to be b minus x2, a plus x1, and then divided by 4ab. Moving on to the third one, same process. If I'm looking at n3, the value of the node at n3 must be equal to 1 and 0 everywhere else. I get the shape function, and finally the same thing for n4. So these are the shape functions. Now that I have those shape functions, I'm good to go. I can start substituting them in to my actual equation. So the first thing I'm going to do is I'm going to define my shape function matrix, which is very similar. And this is where I'm going to ask you guys. Do you guys see the pattern on how we get this shape function matrix? It's just n1, n1, n2, n2, n3, n3, and so on. So how is this shape function matrix n looking for you guys? If I were to give you guys a random element, let's say with 5 nodes, makes no sense, but 5 nodes. Could you guys figure out what the n matrix is if I give you all 5 shape functions? Probably. It's simple, because if we add that additional node, we would simply have n5, 0, 0, and n5. If I gave you 6 nodes, it'd be an n6, 0, 0, and 6. So hopefully that makes sense. You guys can start seeing the similarities between the shape function matrix and the shape functions. Now, once we move into our B matrix, it gets a little bit more complex. Now, just like the shape function matrix, as we can see, the first 2 rows or columns are just n1. Second 2 columns are n2. The next 2 columns, n3. Well, the same thing really happens in the B matrix, where we have the first 2 columns, n1, second 2 columns, n2, third 2 columns, n3. So this is why I tried to keep them in color, because it's very easy to see the pattern that we do. We do the partial of n1 with respect to x1, partial of n1 with respect to x2, and then down here we have partial n1 with respect to x2 and then with respect to x1. And this is always the same. So if I add additional shape functions, I just kind of add these additional 2 columns all the way through. Does that make sense to you guys? What do you guys think? Is that not too bad? Yes, perfect. All right, good. So in this case, our B matrix is this. And again, it's really gross because it's now a function of x, whether it be x1 or x2. But the nice thing about this one is that it actually has that x2. So this is actually beneficial to us. And the reason why is because we can now model bending. If we were to look here, that first column there, or sorry, that first row, that's the strain in the E11 direction, or the E1 direction. So that's going to be our longitudinal strain. And it's a function of x2. So it means that the strain changes throughout the height of the element, which is great because if we deal with a beam and bending, right, we know that it's compression at the top, so a compressive strain, and then as we move down, it switches to tensile strains. That can actually be modeled using a linear element. Could you guys model it using a triangular element? A linear triangular element? Well, no, because it has a constant strain. Now, what you guys could do with a linear triangular element is just define a bunch of little elements all the way through, and you guys will be able to capture it. But this is nice because it requires less elements to actually capture bending. So from there, we can find our stiffness matrix. Again, same formula as before. C depends on if plane strain or plane stress is assumed. And assuming a constant thickness into the page and plane strain, we get this equation right here. This equation right here. Now, going back to what Nathan was saying, we can solve this. This is no problem. If I were to throw this into Mathematica, and I were to define what A and B are, as well as my Young's modulus and my Poisson's ratio, so basically if I were to define the element geometry and the material properties, I can solve for my stiffness. It's no problem. The only difference is when I were to throw this into Mathematica right here, this may take 5 minutes to run. And that's for one element. One element. So what we're going to do next lecture is we're going to actually find a way that we don't have to integrate at all. Isn't that beautiful? We can solve for the stiffness of a matrix without integrating. So that's what we're going to do next lecture. But right now we're saying that this is the actual formulation. If I were to find any sort of element, this is the formulation. The tricks that we do to get rid of integration, that's what we'll discuss next lecture. But if we were to look at this, it's again the same thing as before. We have transpose of B, we have our C matrix, and then we have B. Now, question to you guys. What's going to be the size of this stiffness matrix for a linear quadrilateral element? What are you guys thinking? What'll be the size of this bad boy right here? 8 by 8, you guys are all correct. Yes, this is an 8 by 8 matrix. We have 4 nodes. Each node has 2 degrees of freedom. Therefore, we have 8. Hopefully that makes sense. Moving on to the nodal forces. Again, this is the same thing as before. The only difference is n has changed. So we just substitute our new value of n, integrate over the volume. We can find our nodal forces. Same thing for the traction vectors. Again, only thing that changed is n. We make the modifications for n, integrate over the surface. We're able to get our nodal forces due to traction vectors. Now, when we dealt with linear triangular elements, we said that their major drawback was constant strain. Remember, the B matrix is constant, therefore the strain was constant throughout the element. Linear, so I'm making an emphasis here, linear quadrilateral elements have a problem too. And it's called shear locking or parasitic shears. All right, so you're saying, all right, well, hold on one second. What is shear locking? Well, let's take this right here. Let's say I have an element and I were to put it into pure bending. Okay, pure bending. Well, we know that the behavior is going to be something like this, right? It's going to be something like an Euler-Bernoulli beam. The problem with linear elements is we are assuming a linear approximation, aka a straight line, between the nodes. Therefore, our element behavior is actually going to look something like this. Now, the problem with this deformation is it's thinking that there's shearing. It thinks that it's shearing. So what happens when we model something in bending using these linear elements, some of the energy that would normally go into bending, the expected behavior, would actually go into shearing. And this is very obvious. If you guys go look at the B matrix, the shear strains are a function of x1 and x2. So what happens is this results in a stiffer element. So what happens is if you guys are going to model something in bending using these linear quadrilateral elements, it'll result in something being too stiff. It won't be as flexible as the actual elements. And again, this is because some of that energy that is supposed to go into bending the element is actually going into shearing the element. So this is why we call it shear locking or a parasitic shear. Now, how can we avoid this? Well, one is to use many little linear elements, so increase your mesh size. But another thing is to use a higher order element. Again, the problem with this is we couldn't model that curved surface. But if we were to use a quadratic element, well, we know that the approximation is now parabolic. Therefore, we can actually take into account that curved surface. So that leads us into quadratic quadrilateral elements, which is a real mouthful to say, but it's actually the same process as before. So at this point, I probably don't even need to teach you guys. You guys will know exactly what to do. So if we're looking at the quadratic quadrilateral elements, we say, all right, well, we have an element. The only difference between this one and the last one is we just have more nodes. In this case, we have 8 nodes. We're saying, all right, well, it's not too bad. How about the dimensions? Well, again, we're going to say that it has 2a and 2b for the width and the height. And since it's quadratic, we are going to use a quadratic approximation function. Now, this is where things get really yucky. Because just like before, we stopped at a3 times x1 times x2. Now we're adding on a4 times x1 squared, a5 times x2 squared, a6 times x1 times x2 squared, and a7 times x1 squared x2. Yuck. No one wants this. So now my question to you guys really quick. I have 8 a coefficients now, one for each one of the nodes. How many shape functions am I going to have? How many shape functions am I going to have if I have 8 a coefficients? 8? You guys are geniuses. See? You guys don't need me. This is nice and easy for you guys. So again, I'm saying, all right, well, that approximation is great. It's fun, but I want the nodal displacements. So I can model those nodal displacements with each node having 2 degrees of freedom, and I can change my displacement function into u1 times n1, u2 times n2, u3 times n3. So again, it's a function now of the nodal displacements as well as the shape functions. The question is, well, what are the shape functions? Well, same process as before. We have our elements, and our shape function must satisfy those two conditions. At that particular node, it has to be equal to 1, and at every other node, it has to be equal to 0. So if I'm dealing with n8 right now, it has to have a value of 1 at node 8 and a value of 0 at the other nodes. And it's going to look something like this. Very, very gross. The equation to model that, this yucky thing. Now remember that this is just 1, but we actually have 8 shape functions, as you guys just told me. Therefore, these 8 shape functions are actually going to be the following. And as if things aren't bad enough, remember that with those shape functions, we then have to determine the B matrix, which is all those partial derivatives of all those shape functions. But again, do you guys see how this B matrix is basically the same for every element? It just depends on how many shape functions that you guys have. What do you guys think in the chat? I want to make sure that this is nice and easy for you guys, because once you guys know the B matrix, everything else is piece of cake. You guys good with the B matrix? Thumbs up? Thumbs up? Maybe thumbs down? Iffy? No. No? Maybe not? Yes? I got one yes. I'm trusting you guys. Trusting you guys. Because remember, if this is more complex right now, it's easier to try and get it out of the way now before trying to analyze it later. So now we know that our B matrix, as well as our shape function matrix n, all we need to do is substitute them into our stiffness matrix. Again, it's 2D, so remember that plane stress or plane strain. This results in a 16 by 16 matrix. Nodal forces, same formula as before. The only difference is our n vector has now changed. And again, proportional to the degrees of freedom of the element. So just like before, this was 2D. A 16 by 16 matrix for one 2D element. What about 3D? Well, the 3D version of the quadrilateral element is called the brick element. Sounds muscular, a brick element. So our brick element has two, just like before, two geometric orders, linear and quadratic. And the linear one has 8 nodes, with each node having 3 degrees of freedom. The quadratic brick element has 20 nodes, each with 3 degrees of freedom. So question for you guys in the chat, what is the size of the stiffness matrix of a quadratic brick element? 60 by 60, right on. Yep, 60 by 60. And again, that's one element. So that's 60 by 60. Imagine how many components that is. It's 60 times 60. And then each one of those components afterwards, you have to integrate twice. This is why integration becomes a real problem. So Mahmoud asked a good question. It was direct, so you guys can't see it, but it says, which is better for computational time? Many linear elements or less quadratic elements? And this is where the finite element method becomes iffy. It depends on the situation. Sometimes it's better to have linear. Sometimes it's better to have fewer quadratic. And this is that thing, when we looked at the project, one of the things it talked about was mesh sensitivity. That's exactly what you do there. You start examining the mesh. Should I use quadratic? Should I use linear? Stuff like that. Now, one of the things that you're going to have to keep in mind is that when we're picking between linear and quadratic in real life scenarios, it's not really about computation time. Of course it helps, but usually what happens is the geometric order is independent of computation time. Then what you do is you say, all right, I'm using a quadratic element, and you start shrinking it until the results converge, and then you have to figure out, okay, when do I stop shrinking it to save computation time? Now, the reason why I said it's kind of independent is because of this. When we're dealing with nonlinear materials or nonlinear geometries, most of the time you guys will have to use quadratic elements. For instance, if we're dealing with concrete and you guys were to use linear elements, it's very difficult to converge when cracking starts happening. Stuff like that. So what we're going to see is that the selection of quadratic or linear will depend more on convergence rather than computation time. So does that make sense to you guys? Does that answer your question, Mahmoud, at least, hopefully? Yes? Perfect. And don't worry, we're going to discuss all of that once we start getting into the later half of this course. So the general thing, if I can give you guys right now one thing to take away from this lecture, it's this. The process has always been the same no matter what element we selected. We find our shape functions, from there we find our B matrix, and then from there we find our stiffness matrix. Hopefully that makes sense to you guys. And that is it for the first part. So that's it for the kind of the lecture components. I say that we're going to take, how about a 10-minute break? Give you guys a nice easy rest. And then at 10:05, we'll come back and we'll get into ABAQUS. I know you guys want ABAQUS, right? Sound good to you guys? If there's any questions, I'll be back in about 5 minutes. I just got to refill my water. So I will see you guys in 5 minutes for questions, but the lecture will resume at, let's say 10:05, okay? Sound good? Perfect. All right, guys, I'm back. So if you guys have any questions about what we covered, just let me know. And we'll begin again in a couple minutes here into the actual content stuff, which will be ABAQUS.
Can I ask a question?
Yes, of course.
It's just about the way in which you determine the shape function coefficients. Yes. I know that we did it for 1D, but maybe if you could jog my memory. I wasn't familiar with those.
Of course.
I wasn't familiar with those diagrams that you had where you kind of used like N1 or N2 as another axis and then determine some sort of distance.
Yeah, so that's just the actual how they look, but I'll show you exactly how we do it. So I think that'd be the best. So I got Mathematica up. I put the screen back, right? You guys can see Mathematica?
Yep.
Perfect. So the first thing I'm going to do is I'm just going to clear everything. Just so nothing goes crazy. So what we did is we said that our approximate, so I'm just going to go uapprox, let's say for a quadrilateral element, okay? We said that it was going to be A0 plus A1 times X1 plus A2 times X2 plus A3, where's the time? times X1 times X2. So this is what you guys do. You guys first start off with the approximation function. Now, what we're going to do is we are going to, actually, I'm just going to call this displacement just so that I don't have to write as much. So what we're going to do is we are going to find out what this is at very specific points where the nodes are. So what I'm going to do is I'm going to say equation 1 is going to be that displacement function at node 1. Now, we know that node 1, if I were to load back up at the PowerPoint, if I can find out where it was located at -a, -b. And I'll show you exactly where these coordinates are. Right here. So since this is 2a, this from here to here is going to be a magnitude of a, right? And since this is 2b, this will be a magnitude of b. So this point right here will be -a, -b. This point right here will be a, -b, etc. So equation 1, we're going to say is when x1 approaches -a and x2 approaches -b. And what I'm going to do is I'm just going to create 4 equations, one for each one of those nodes. So I'm going to call this just equation 2, equation 3, equation 4. Now I just have to modify these. So this goes to positive a, and then right here, node 3, they're both positive, and then right here, b is positive. So I just created 3 equations. So just like before, we're going to solve the system for A0, A1, A2, A3. So I'll put my 2 brackets here since we're doing multiple inputs. So we're going to have equation 1. Well, equation 1 was the displacement at node 1. So this is equal to the nodal displacement U1. Does that make sense?
Yes.
Perfect. Equal to U1. Because again, where did the PowerPoint go? This will maybe help. At this point, I put in the coordinates for this point. And we know that since this point's a node, it has a nodal displacement U1. Hopefully that makes sense. So I'm going to do that for all of them. So if I come down to equation 2, well, that was at the location of node 2. So this will be nodal displacement U2. equation 3. This was at nodal displacement u3. And finally, equation 4 was at nodal displacement u4. And again, I'm solving for a0, a1, a2, and a3. So I just got to make sure that I inputted things correctly. So if I were to solve it right now, I get what my coefficients are equal to. So if I were to go with my displacement function, it is now a function. Oh, I didn't store them. That's why. A0, a1, a2, a3. So now my displacement function is now a function of my nodal displacements after I do that. But what I want is I want my equation in the following form, is I want the coefficient in front of u1. The shape function 2 is going to be the coefficient in front of n2. The shape function n3 is going to be the coefficient in front of n3. So after I get this, I just say that n1 is going to, n1 is going to be the coefficient of my displacement function in front of u1. And I would just repeat this for all the other ones. So n2, n3, why don't this go down? n4, this will be u2, u3, u4. So if I were to run it, I now get this, and if I were to full simplify them, I get the exact same thing that we had back in the PowerPoint.
Okay. Yeah, I see what's going on.
Perfect, perfect. And hopefully that makes it clear for everybody else yet.
It does make it clear. It just, it helped to see it in the context of the quadratic element.
For sure.
Or the full process. So then, or not quadratic, quadrilateral. Is the x2d, is that just kind of...
That's our displacement within the element itself.
Within the element, so it's just kind of a generalized term.
Exactly. So, yeah. Okay, so once we figure out those nodal displacements, we can then figure out what the displacement in the element is using that x2d.
Okay.
Perfect. Perfect. So I was going to address this right now. So what we're going to do is we're going to look at the assignment. So the assignment has two things. One is I want you guys to take basically a square or rectangle. And I want you guys to simply just rotate it. So you guys are already given the displacement functions for rigid body rotation. It was covered back in lecture 2. But I want you guys to take those and figure out what exactly the strain components for this would be. So this is nothing new. And then what I want you guys to do is I want you guys to model this in ABAQUS and figure it out. What's going to be a little bit funny is that rigid body rotation should have no strains. All I'm doing is I'm taking a square and rotating it. I'm not stretching it or anything like that. What you guys will find is the small strain components will report some strains. So what I want you guys to do is I want you guys to find the theoretical strains after we rotate this. And then I want you guys to go into any finite element program you want. So it doesn't have to be ABAQUS. And I want you guys to rotate that too. Now in ABAQUS, there's this very specific feature. And if you don't activate it, you guys will have strains just like you would before. But then what I want is part C is I want you guys to enable something called nonlinear geometry. And I'll show you guys what that is in ABAQUS. When I enable it in ABAQUS and I rotate it, well, then I have no strains anymore. So that's going to be one of the first things. The second thing, and this is like the most classic FEA thing possible, is the second question here. We're using any finite element program. So I'm not limiting you guys to ABAQUS. You guys can use whatever you guys want. Model the cantilever beam shown below. So I want you guys to use 4-node, plane stress, quadrilateral, full integration elements. Now this full integration elements is something that we'll talk about next lecture. I'll show you guys how to do it, but we're going to talk exactly about what that is next lecture. And a constant thickness into the page for both a Poisson's ratio of 0 and 0.3. So just a cantilever beam with a point load at the end. So now that I made it very clear that this assignment's using a finite element program, I'm going to address the question that I got a lot. A lot of people don't have access to ABAQUS yet. And that's because IT, for some reason, I don't know why. Don't blame me, this is IT. They changed it this year so that anyone that wants to use ABAQUS has to be approved by them. And this was a problem because I was constantly getting emails. Is so-and-so in your course because they want access. So just on Friday, I gave them the course list. So everyone that's in the course, so they should know now. So I'm going to follow up with IT. But if you guys can't get ABAQUS going, please message IT and CC me in it. And then what I'm going to do is I'm going to reach out to IT myself and include all of the names so that they can really get on it. Now, I want you guys, again, not to stress. I don't want this course being stressful. If we look right here, there's going to be two things. If we were to look at the due date for this assignment, Nathan, this is the full version. So if you guys have the student version working, this assignment will be just fine. It's when you guys get to that final project, you guys will want the full version. All right? The full version. And the reason why is because the student version is limited to 1,000 nodes. So if you guys are doing an actual good project, well, you're probably going to go over that. But in regards to this assignment, it's due on the 22nd. So of course, next week is reading week. I'm not going to make the assignment due on reading week. So there's 2 weeks for this assignment. Now let's say that it's the middle of reading week and I'm still talking to IT and you guys still don't have ABAQUS yet. I'm going to extend the assignment. I'm not going to make this a big stressful course. Hurry up and get ABAQUS or else can't do the assignment. Don't worry. I'll extend the assignment as needed if we need to. Okay, so I'm going to make sure that everyone has ABAQUS. Everything will be good to go. So again, if you guys don't have ABAQUS, please contact IT, CC me so I know, and I will kind of get on their ass to make sure that you guys all have ABAQUS. The assignment won't be due if you guys don't have ABAQUS. I'll make sure that you guys have ABAQUS. So is there any questions about that? Are you guys relieved somewhat? I know that it seemed to stress a lot of students out. Don't be stressed. That's not this course. That's for the other courses, not this course. All right, perfect. So now we're going to get into ABAQUS. And I thought that the best way to show you guys ABAQUS was to model the actual assignment question, which I got rid of. So let me go back into it so I can show you guys what exactly we'll do. Come down here, assignment 4. So what we're going to want to do, and I'll zoom in here, is we're going to want to model a cantilever beam. So it's just basically a rectangle. We're going to fix the left-hand side, and we're going to apply a point load at the other side. Nice and easy, right? We're going to have a Young's modulus of 10,000 and a Poisson's ratio of 0 and 0.3. So, a good question. So with the instructions on E-Class, that would be the full version. If you guys were to go to E-Class and go to these ABAQUS instructions, this is for the full version. This is not the student version. This is the full good-to-go version of E-Class, of ABAQUS, which is why IT is kind of being a pain in the butt with it. All right, so now we're going to get into the actual ABAQUS. We're modeling a cantilever beam. We know the material properties as well as the geometry. So actually, I'll just pull up the material properties again. 10,000 for Young's modulus. We'll go with Young's Poisson's ratio 0.3. And we know that the beam is 5 units long, 1 unit high. All right, guys? So let's get into ABAQUS. So ABAQUS, the best way to model something, at least what I've seen, is just go through the modules. So if we click this module right here, we have part, property, assembly, step, interaction, load, mesh. You guys won't use optimization, don't worry about that, and job. And once you guys get to job, that basically just means submitting your analysis, letting it run, good to go. So we want to get to this job module. And if you guys follow these steps, it's very easy to get there. So we're going to start with the first one, which is part. Now again, part is where we create the specific pieces we're going to use in our model. Let's say that I have a beam, a steel beam, and it's connected with bolts. In the part module here, this is where I'd create the beam as one piece. I would create the bolt as one piece, etc., etc. So this is where we create the individual parts that we are going to use in our model. Now, when we look at our particular model here, we have a cantilever beam. So our part is actually going to be the beam itself. What's nice for us is that this beam, it's just a beam. So we only really need one part for this model. So how do we create that part? Well, it's simple. We can go to this button right here that says Create Part. Now down here, we also have something called Part. So I can either click this button, which will create a part. It just appeared. Where did it go? It's behind the chat. That's why. It always appears on the second screen. You guys will get this menu right here if you go Create Part. Now, instead of clicking the button, we can double click Parts right here. Now I got a question. Is my screen pretty easy to see? I'm going to try something, and you guys may hate it, but I think it might make it easier. I find that the screen is pretty hard. Yeah, it's pretty small. All right, so let's go display. Let's see if I can zoom everything. So when I do this, it usually makes a mess, but we'll see what happens. What does this do? That didn't really help. It says it detects. I did it before when I was doing videos. Oh, it's because I did it to the wrong screen. All right, let's see if this works. That's almost too big. It kind of looks ugly, but why can't this go? Let's get rid of that. How's that? Is that better? Hopefully it's better. Perfect, perfect, perfect. All right, so again, if we want to create a part, we can go to this button right here that says create part, or we can go over here to the actual parts. So I'll just click this button right here, and again, it pops up over on the other side. I'm not too sure why. Where did it go? This is the problem with having too many monitors. You start losing track of everything. Where is it? It says fill out the dialog box. Where did it go? I wonder if this is a result of me making everything too big. All right, hold on. Let me restart ABAQUS. Maybe making it bigger may have messed everything up. All right, round 2. And what I'll do is I'll put it over on this monitor, switch the sharing. Actually, no, that'll just make everything worse. All right, chat's going down. It's going down. So let's try creating a part really quick. All right, so the part menu comes up now. You guys can see it? What a hassle ABAQUS is. But I don't even know where my chat is now. I fix one thing, but then create more problems. All right, let's try and go back to chat. All right, I got the chat. We can finally begin. What a lot of fun. So when we're creating our part, of course, you got to name the parts. And this mainly comes down to when we're dealing with multiple parts. For us, it's not a problem because we have one part, which is the beam. But if we're dealing with, let's say, again, the steel beam with all the nuts and bolts, well, we're going to want to label them nut, bolt, beam, etc. So for our part name, we'll just call it beam. Nice and simple. Now, the modeling space, we can either select 2D, 3D, or axis symmetric. So when we're dealing with this particular problem, when we pull it up, we have a 2D beam. So we're going to go into the 2D modeling space. We're going to want to keep it deformable, and for our base feature, we're going to want to keep it a shell, which basically means it's going to actually be a 2D element. If we were to do a wire, well, this would be like our bar element that we dealt with before, but we're going to want to keep it shell. Now, our approximate size, again, this doesn't matter. You guys can have it as 1,000, 2,000. It doesn't matter because you guys can still draw. So I'm going to click continue, and we are given this particular drawing space right here. So we can zoom around. And again, right here, this is where they ask for the approximate size. So this grid right here is 200 long. But again, I can draw outside of the grid. It's not really a problem. So when we're dealing with this particular thing, we know that we're dealing with a rectangle, right? We have a beam. It's a rectangle, nice and easy. So what we can do is we can either pick a corner or we can actually input the coordinates down below. So what I'm going to do is I'm going to enter the coordinates. I'm going to say that the bottom left corner starts at 0, 0, right at the origin there. Now we know that our beam is 5 units long and 1 unit high. So the x and y would be 5, 1. Remember, 5 long, 1 unit high. So if I were to enter that, I get this. I get my beam right here. Now, this is all I want, right? I just want a nice solid beam, which is a rectangle. I'm good to go. So what I can do is I can exit out of the drawing the rectangle command. And then once I'm done with my beam and I'm happy, I simply click done. And it gives me my part right here. So this is going to be the beam that I want to do all my calculations on. So when it comes to the part module, we're actually good to go. The part module is just where you define the geometry of your part, nothing more. So with the part module done, I can click this and I can go down to the next thing, which is going to be the property module. And in here, this is where I start assigning material properties to the parts I created. So if we look up here, the first button that you have says create material. Now, if I were to go down to the side, we also have materials right here. So we can either go here or here. They're going to give you the same menu. So if I click right here, it appears on the other monitor, but this is the menu that you guys get. If I were to double click over here on the side, same menu. So the first thing that's going to ask for is the name. So what do we want to call this material? Well, let's just call it, I don't know, what do you guys want to call it? We'll call it concrete, even though it's definitely not concrete. We'll just call it concrete just to show you guys what it does. Now here is where we can define the different material behaviors. So general, this would include things like density. This actually has to do with the physical properties of it. Mechanical, this is where we start dealing with those mechanical models. So for us right now, we want to deal with elastic things. We're not going into plasticity yet. We want elastic. So if I want elastic things, I go mechanical, elasticity, and then over to elastic. So if I were to click elastic here, it says what type of elasticity? Well, we want isotropic. Remember the other ones that we covered, orthotropic and isotropic, they're all mentioned here. So if you guys want to do those, we have the option to, but we're sticking with an isotropic material. Now it's going to ask for two things. First is the Young's modulus, and the second one's the Poisson's ratio. Now these were two things that we were given in the question. We said the Poisson's ratio was 10,000, and the Poisson's ratio, or Young's modulus 10,000. Poisson's ratio, you have to do the analysis twice in the assignment, one for 0 and one for 0.3. So for this one, we will just go 0.3. Now, our material defined in the assignment, it is just elastic. We're not dealing with any plasticity. We're not dealing with any sort of mass, anything like that. So this is all we actually need to define. So again, we defined an elastic material. We defined the Young's modulus, Poisson's ratio. We're good to go. So we can come down and click OK. So if I were to expand this, I can now see that I have a material created under my material tab, and it's called whatever label I gave it. So I called it concrete. It says it's concrete. If I were to expand my parts tab, it shows all the parts that I created. So I now have my beam under there. So now that I created both my beam and I created my material, the next step is to take that material and assign it to the beam. So there's two things that we actually have to do. The first is create a section, and then the second one is actually assigning the section to the beam. So what we can do is we can come down here to the sections command, or we can go down to the button right below the material, which says create section, and you guys are given this menu right here. So we're going to have to name the section. Well, we know that we are creating a section for our beam. And the reason why we're doing this is because when we created the part, we only defined the part geometry in the plane. We didn't define anything into the plane. So right here, this is where we start dealing with that. So the first thing that we're going to say, well, what kind of section do we want to create? Well, today we talked about solids. So we're going to keep it solid, and we're going to keep it homogeneous, right? Just one material, not composite materials. So solid and homogeneous. And luckily for us, these are selected by default. So you guys just come into here, you guys name your parts, you go continue, and it's going to ask you for two things. The first one is, what is the material behavior of this section? Well, since we only have one material defined, which is concrete, that'll be my only option. And the second one is the plane stress / strain thickness. So this is that thickness into the page. So if my beam was, let's say, 2 meters long into the page, I would change this 1 to 2. But in the assignment here, it says that it just wants a unit thickness into the page. So we can actually just keep it as 1, which is set by default. So we're just going to go OK. And now we've created a section called beam. Now this section here has the material properties as well as the thickness into the page. And what we're going to do is we're going to take that section now and apply it to our beam. So I come down to the next button, which says Assign Section. So I'm going to click this, and down here it says Select the regions to be assigned a section. Well, I want to assign it to our beam. So I'm going to click the beam. It gets highlighted. I go done. And then this menu pops up that says, what section do you want to assign it? Well, the only section I've created is beam. So therefore, that's my only choice. If I created multiple sections, I would have different sections right here to choose from. Since I only have the one, I click beam and I click OK. Now, here's the key, the secret. If you guys did this correctly, this will now turn this kind of aqua blue. I don't know what they call it. I had asked this continuum mechanics kids to help me out, and one of them said seafoam. I have no idea what seafoam looks like, but I guess we'll go with seafoam. If you guys did it correctly, your part will now change colors. All right, so now this is great. We defined a part, and we've also implemented the material behavior into that part. So now we can click here, and we can go to our next module, which is the Assembly tab. So again, this is the spot where you're actually going to analyze an ABAQUS. So if I were to run ABAQUS right now, it's analyzing this, which is nothing. Once we create the parts, we bring them into the Assembly tab, and just like it's called, we assemble them. So in this case, we only have one part to bring in, which is going to be our beam. So to do that, we go right here, which says Create Instance. Now, instead of going Create Instance, we can come down here to our Assembly tab, expand it, and under Instances, we can double click this. So you can either double click Instances, or you guys can just click Create Instance. It'll bring you to the same menu. So if I click that right here, this menu pops up here, and it says, what parts do you want to bring into our model space? Well, the only part we've defined is our beam. So I can click my beam, which it does by default, and we can click OK. So now we brought this beam into our modeling space. Now, what's the difference between the parts and the assembly? Well, the parts are just those individual parts. The modeling space is where we analyze everything together. So if I wanted to, I can add a second beam here for fun, stuff like that. So you guys see the difference between the parts and the actual assembly space. Now, what's nice for us is that when we're dealing with our beam here, we only have the one part. Therefore, our model space is just going to be that one beam. That's it. Nice and easy. So in terms of assembly here, we're actually good to go. That's all we needed to do is just bring in our one part because we're only analyzing the single part. So what I can do is I can move on to the next one, which is going to be the step module. The step module. If I were to come down to my model tree, that's right down here, so I can expand it right here. And as we can see, we only start off with an initial step. Now, the initial step is where your initial boundary conditions go. So if something was fixed, this is where I'd apply that condition that something is fixed. This is not where the loads go. So in general, the step command is your sequence of events. So if I were to take this beam and I were to load it axially, like pull it, and then after I pull it, I were to put a load downwards, that would be two different steps. The first step is loading it axially, and then the second step is pushing it down. So the steps are basically the sequence of events in our loading scenario. If I were to do a cyclic loading where I pull it, and then squish it, and then pull it, well, each one of those motions would be its own step. Now, when we're dealing with this problem right here, if I were to go back, come back down here, we only have one sequence of loading, and that is applying our load here at the end. Therefore, for this particular problem, we only need the one step, which is just simply loading that point load. So what I'm going to do is I'm going to double click step, or I can come up here that says create step, and you guys will get this menu. Now, we're going to have to label our steps so we don't get them mixed up. But for us, since we have the one step, we can name it whatever we want. But I typically like to name it what we're going to do. So I'm going to call this step apply load. All right, apply load, and we're going to keep it a static case. So this static RIX, don't be confused. We'll talk about that a little bit later. We're just going to keep it static and general. So I'm going to click continue, and you guys will get this menu right here. So this is basically one of those menus that deals with incrementations and nonlinear geometry, stuff like that. So this is going to come into play when we start talking about nonlinearities a lot. Since we're doing a linear elastic analysis, it's not going to make much of a difference from here. But in your guys' assignment, I want you guys to go back to your assignment. In the first one, if we look at part C, it says repeat part B, which is modeling this in an FE program, after enabling a geometric nonlinearity option. A geometric nonlinearity option. In ABAQUS, this is in the step command. This right here, NLGeom, this stands for nonlinear geometry. So what you do is you would just simply click this to on. So if you guys are doing the assignment, the first time in part B, you keep it off, you find your results, then you move on to part C, you keep the exact same model, you just change this nonlinear geometry to on. And this is something that, again, right now, linear elastic, it's not going to make a difference whatsoever. When we start dealing with nonlinearities, such as plasticity models, this is going to become very important. And chances are, if your model is very plastic, it won't run if this is off. So it's something to keep in mind. So we're just going to keep it to on. It's always good to have it on. There's no reason to have it off, really. And we can go into incrementation. So this is something that we'll also discuss later. So one of the things that we're going to see is that the finite element method's an iterative process. If I wanted to apply 100 kilonewtons, chances are I don't just go from 0 to 100 kilonewtons. I apply 10, then I apply 20, 30, 40, etc. That's what happens in this right here. This step right here is we can change the incrementation of the load and how we apply it. But for us, we can just leave it the same. We actually don't really need to worry about it too much for linear elastic problems. So we're just going to keep everything default. The only thing I did was I turned on nonlinear geometry. Again, for this problem, I don't need to. It's just a good habit to start changing it to on. So I'm going to click OK. So now I have two steps, my initial step, and then after that, I start applying my loads. So the steps are good to go. I can come down to the next property, which is interaction. Now this occurs when I have more than one thing interacting with each other. But in this particular case, I just have a beam. That's it, just a beam. There's no other parts hitting it or anything like that. So in this particular case, there is no interaction. We don't have to worry about that. But we will talk about that later, so don't worry. So I can skip that module and go down to the next one, which is loads. So this is where I define my boundary conditions as well as my applied loads. Okay, boundary conditions and applied loads. So right here, the first button says create load, and the second button says create boundary condition. Now, if I were to scroll down here, I have the option in the model tree here too. I have loads and I have boundary conditions. So if we were to look at our problem here, I have one of each. I have a fixed end over here, which would be a boundary condition, and I have my load here, which should be my point load. So what I'm going to do is we'll do the boundary condition first. So I can go this button here, create boundary condition, and you guys will get this menu right here. Again, we're going to have to name what our boundary condition is. Let's just call it fixed end because that's what it is. Now, if we're dealing with these initial boundary conditions, it's a good force of habit to put it in the initial step. Remember that the initial step is where all our initial boundary conditions are, which is the case here. So I go initial boundary condition, and what I want to do is I'm going to go displacement. You guys can go up here if you guys want. We'll talk about that a little bit later. But I find it easiest just to go displacement / rotation because that's the boundary condition that we have. We have a displacement boundary condition. So I'm going to click here. I'm going to go continue. And then it's going to say what region of the beam do you want to apply this to. So what I'm going to do is I'm going to click this edge right here. We can see that it now highlights and I can click done. After you do that, this menu will appear right here and saying, all right, which directions do you want to constrain? So I want to limit all the horizontal direction. I want to limit all the displacement in the vertical direction. Now, question for you guys. Do I want to limit the rotation? So this right here, this UR, this is the rotation about the Z-axis. Do I want to limit, or should I click this button right here? I hear one yes. What do you guys think? Yes? So my question is, let's go back to the PowerPoint. When I did my degrees of freedom for the system, did I have a rotational degree of freedom? So Mahmoud is right. If U1 and U2 are fixed, it won't be able to rotate. And we look at the theory here, there is no rotational degree of freedom. So in ABAQUS, I don't have to click this. If you click it, it'll give you the same results. But if you click it when you're running it, ABAQUS will give you a little warning message that says, hey, you clicked something that doesn't apply. So it'll still run it, and ABAQUS will know what you were trying to do, but you don't need it. So we only have to limit these two right here. So we're going to click OK. And as we can see, we now have boundary conditions applied to this end of the beam. So that's our boundary conditions. Now we can go into our load. So if I were to go load right here, we are get this menu right here, and we can't apply a load in the initial step. And this makes sense because again, the initial step is just for our boundary conditions. So what I'm going to do is I'm going to change the step to my apply load step that I created, and now I have the option to define anything I want. So first of all, we have to name it. Well, let's just call it axial load. Axial load. And what type is it? Well, we can apply a concentrated force, moment, a pressure, anything like that. Well, we know that this is just going to be a concentrated force. So I'm going to click concentrated force, continue. It's going to say, where do you want to apply this concentrated force? Well, I want to apply it right here at the end. So I select there, it's highlighted, I go done. And then you guys are given this menu right here, which says what is the components of the force in the horizontal direction and what is the components of the force in the vertical direction. So we know that it's an axial load, so just vertical. So the horizontal force is going to be 0. And the force in the vertical direction, if we look at the assignment, we're giving it as 1 units of force. Now, if I were to go 1 unit of force and go continue, we see that it goes upwards. But we know that we actually want our load to go downwards. So this is one of the nice things about finite element programs, is that if you're unsure about sign convention, well, it'll show you what exactly is going on. So if I want to modify this, I can just expand my load command, and I can see that I have my load, axial load defined. I can double click it to edit it, and I can simply add my -1 in there. So if I go continue now, it now switches this to a downwards force. So it says, if we do not close the rotation, how do we restrain from buckling? That's a good question. What do you guys think? Buckling is its own separate analysis in ABAQUS. We'll talk more about buckling in the instability, but there's actually different things that you consider when you deal with buckling. And we'll talk more about that later. It actually is one of the different steps. So if I were to go linear propagation, buckle, it's a different thing. And yeah, Omen's right is that we don't have the imperfections too. So again, buckling is something we'll discuss later on. Don't worry about it too much right now. So now we have everything defined. Everything. We have our steps, we have our geometry, we have our material properties, we have our boundary conditions, our loading. What are we missing? What are we missing? Because if I were to run this right now, ABAQUS would say, ha, you can't do that. Mesh. Aslam is right. Mesh. Oh, you guys are all so smart. Mesh. So remember that the whole thing that we did this lecture was we discussed shape functions and the stiffnesses of elements. If I were to look at my beam, well, right now it's just basically AutoCAD. It's just a square. What I need to do is I need to apply a mesh, or in other words, I need to create those elements and those nodes. So if I were to go to my module right here, the next module I have is mesh. Now, you guys will get an error if you guys try to mesh this right away. So if you guys go to the mesh module, by default, ABAQUS will try and mesh your assembly. So if I have multiple parts in here, what ABAQUS will try and do is give them all the same mesh. And you never really want that. You want to mesh things individually. So rather than meshing the assembly, we want to mesh our specific parts. Our part being our beam. So we want to apply a mesh to it. So there's a couple things that we need to do when we're applying a mesh. The most easy way to apply a mesh is this button right here that says seed part. And what this will do is this will take an element size and try and apply it to the whole beam. So if I were to go seed part right now, this menu pops up right here, which says approximate global size. Now remember that each one of our elements, our quadrilateral elements, were squares. What this 0.5 is basically the length of one of those squares. So if I were to go 0.5 and my beam is 5 units long and 1 unit high, we know it's going to look something like this. So this would actually be one of the elements right here. This would be one of the elements right here, etc., etc. So if I were just to use ABAQUS's default controls and I were to mesh the part, how do I do that? Well, I click this down here, go OK, I get this mesh right here. Now this mesh right here, probably not the best mesh. And that's going to be the goal of the assignment, is you guys are going to keep decreasing decreasing, I don't know why I couldn't say that, decreasing this mesh size and see how the results start to change once you start decreasing it. Now, one of the things I can do is say, all right, well, rather than applying a global mesh which tries to create square elements in every direction, I can specify the elements in each direction by seeding the edges. So what I can do is I can go seed edges instead. And for instance, I can seed this edge right here. I can go done, and then I get this menu right here. So the question is, it says I can either seed it by the size. I can specify the actual geometric size of the element, or how many elements I want over that length, or I can specify the number of elements I want over that length. So let's say that I want 3 elements in the vertical direction. 3 elements. I would click 3, and I would go apply. Now ABAQUS says, hold on. You've already applied a mesh. If you try and remesh it, it's going to delete the current mesh. We're saying, well, yeah, because that's exactly what we're trying to do. So we can go delete mesh. So now I can see that I have 3 elements in this direction. Now, if I wanted to, I can go, okay, that's good. How about this direction? How many horizontal elements do I want? So how many horizontal elements do you guys want in the chat? There are no wrong answers. How many do you guys want? 15? All right, 15. So you go 15, something like this. You apply it. Good to go. So now as we can see, we mesh these 2 sides, and what ABAQUS will try and do is create the mesh. So what I'm going to do is I'm actually just going to seed this edge right now so I don't have any problems. This will also be 15. And then this one right here will be 3. ABAQUS may give you some wonky results. One of the hardest things about the finite element program is creating an automatic meshing tool. That's why ABAQUS is one of the few. Those of you that like OpenSeas know that you have to create your own mesh. You have to define the nodes, and you have to go from there. And in ABAQUS, if you guys really want, you guys can create your own nodes and stuff too, but that's kind of out of the scope of this course. So now that I meshed all the sides, I can click this, mesh part. I now have 3 elements, and then I have my 15 elements. Now, what I want to do is I want to show you guys something else. So I'm going to take these 2 sides now, and I'm going to say that, you know what, instead of 15 elements, I want 5. I'm going to delete my old mesh, go OK. Mesh the part, good. So my question is, for you guys, are those elements okay? They're not perfect squares. Is that okay? Yes. So I got a direct message so you guys can see it, but I heard a yes. That is correct. It's definitely okay. You guys can create as many elements as you want, and they don't always have to be perfect squares or rectangles. And we'll discuss more about that next lecture. So I'm going to go back to, let's go 20. We'll make it a pretty fun, and actually we'll just do this as 0.25. So this again applies this seeding in all directions. So we get something like this. All right, so this is going to be my mesh, or should I make it a little bit different? 0.25. Oh, that didn't. Oh, yeah, because it's the mesh. So once you seed the edges, you can't really go back to approximating the other side. So we'll go 4. So this is my mesh. So now we've defined our mesh. So basically each one of the elements. And what we discussed today was the stiffnesses of each one of these elements. So now you guys know what exactly is happening in each one of these elements. But we discussed 2 other things. If I'm dealing with a quadrilateral element and the stiffness matrix, I needed B and I needed C. Now, C, what does that depend on? How do I remember that C could be one of 2 things in 3D, depending on what? The C matrix. You guys remember? This C matrix right here. I guess it says it right here. But plane stress or plane strain, right? So what we can do is we can actually modify these elements for plane stress and plane strain. How do we do that? Well, we come down to this button right here, which says Assign Element Type. So if I were to click this, it says, all right, which elements do you want to modify? Well, we're going to modify all of them. I'm going to click Done, and you guys get this menu right here. And this is the most beautiful menu you guys can have, because everything that you guys learned today is now in this menu. So right now, if we were to look at the family option, we can see that we have plane stress selected. If we wanted plane strain, you just click plane strain. But we want plane stress, so we'll actually, what does the assignment say? So the assignment says over here, plane stress. So by default, ABAQUS has that as plane stress, we're good to go. It says that we want 4 node elements in the assignment, 4 nodes. So right here, when we're talking about geometric order, we can switch between linear and quadratic. So if I want a 4 node element, am I using a linear or am I using a quadratic element? If I want a 4 node element, linear, exactly. If I were to ask you guys for an 8 node element, all you guys would have to do is switch it to quadratic. Nice and easy. So we're going to go back to linear. And now in the assignment, of course, we're dealing with quadrilateral. But let's say that you guys didn't want quadrilateral. Let's say that you guys wanted the triangular elements. Well, you just go into the triangular element tab over here. So everything in this element type section is the goal of today's lecture. We taught you guys everything in this right here. Now, the last thing that it said in the assignment that will probably throw you guys off is this right here. Full integration elements. Now, this is something we're going to talk about next week. All right, next week. But in ABAQUS, to get full integration, right here you have something called reduced integration. And automatically, this will be checked on. What we're going to do is we're just going to uncheck it. This gives us full integration. Now, question for you guys. Does full integration mean that we're integrating the elements? And this isn't something we talked about, so this is complete guesses. What do you guys think? If I unclick reduced integration, am I still integrating the element? What do you guys think? Am I integrating that stiffness? Remember that stiffness that we defined was an integral over the element. And I said that there's a cheap way that we can get rid of integrating. Well, you guys are correct. So even this full integration element still doesn't have any integration. And we're going to talk more about that next week. So we have an integrated element, which sucks. We said we don't want that. So we simplify it into something called full integration. And then if we want, we can simplify full integration into something called reduced integration. And we'll deal with that next lecture. So we're going to uncheck reduced integration to keep it full integration. And we're good to go. So again, right here, quadrilateral elements, triangular elements, geometric order we discussed, plane stress, plane strain we discussed. So we are good to go. Now that we're done the mesh, we look at our next module, optimization. Again, you guys won't touch that. We can go into job. Now, job is very simple. All you need to do is basically tell ABAQUS what you want to call your analysis. But before we can do that, I forgot that I did the most basic mistake ever, is I didn't save the model. So of course, when you guys are doing a model, you want to save the model. So we can save, you go File, Save As. You guys can put it wherever you guys want. So I'll go 665 test, something like this. And that will save your model. All right, that'll save your model. So if I were to open that up, I get this file right here. But if you guys ever worked in a finite element program like ABAQUS or OpenSeas too, same thing. When you guys run in an analysis, the analysis is actually a different file. Now, if you guys just save your model someplace and you guys don't save a directory, what happens is all your analysis files will be thrown somewhere else. So what you guys actually need to do too, to keep track of your analysis files, is you need to set the work directory. So by default, it'll throw it into your temporary folder. So if you guys run an analysis and can't figure out where it is, check your temporary folder. Now, if you guys want your analysis files to go someplace special, well, you guys can select it. You guys can select whatever drive you want and go from there. I'm just going to keep everything in the temporary file. So under jobs, we can either go right here to create job, or we can go right down here to jobs. So you double click it, you guys will get the same menu, and this will say is, what do you want to call your analysis? Well, let's just call this 665 test. I'll go continue. And then from here, it'll just give you options to basically use parallelization, precision, stuff like that. You don't need to touch any of that. We'll just keep it everything as default. We'll go OK. And as we can see in our jobs tab down below, we actually have something called 665 test. Now, it hasn't started yet. To run the analysis, what you do is you right click it and you go submit. All right, right click and go submit. And this will take everything that you've defined in your model and analyze it. So what we're going to do is we're going to click submit. Hopefully I didn't forget any steps. We'll have to wait and see. But when we go submit, it's going to do two things. When it says submitted, it's taking everything that you've defined in your model and it's creating it into something called an IMP file, which is basically just a text-based file that goes over everything that you guys have defined. Boundary conditions, nodes, element type, element geometry, everything like that. After it's done that, it'll go running, which means it's taking that file it created and then it's putting it into the ABAQUS solver to solve it. And then when it's done, it'll go completed. And what we can do is we can actually go right click and monitor it. So as something is running, we can actually check it out. So this step size incrementations, we are going to talk more about that when we talk about nonlinearity. We don't really need it right now. So what we can do is after it's been completed, we can right click and go results. So right click, go results. We now have our model like this, and this looks absolutely terrible. Now, this is the undeformed shape and no stresses. If I want to see the deformed shape and stresses, I just go one down below, which says plot contours on the deformed shape. So if I were to click that right here, I now have my beam. Now, if you guys remember way back when you guys did the stresses of an Euler-Bernoulli beam, you guys will remember that the stress distribution was actually very, very similar. There's only some differences now. So right here, this is the von Mises stress in the beam. But if we look at the assignment, it wants a couple things. So let's go down. It says it wants the deflection at point A, which is down here, and the stress components at point B. How do we do that? Well, we use this command. Oh, I guess it's down below. We can't actually see it. I'll send you guys a video on how exactly to do it. But there's a little button right at the bottom here that's called Curie. And but another way to do it is this. So here's our stresses, and what I can do is I can click Mises, and I can change it to any stress component I want. So let's say I want S11. Well, I click stress component 11, and I can just look at the components over the beam. Now again, I will show you guys exactly how to do it a little bit later on, but since I enlarged my screen, the button's down here and I can't reach it. But there's a button that you click it, and then you just hover over whatever you want, and it'll tell you the stresses exactly there. Now, another thing that it wants is the deflection. So instead of S stands for stresses, we can go down to U. So U is deflection. If I click U, it gives me a couple options. The first is the magnitude. We don't want that. We want the vertical direction. So instead of U, our magnitude or U1, I want the direction vertically. So that would be U2 right here. So then I'm going to go down to that command down here. Again, it's called the probe command. Very fitting, I guess. But you go to that probe command, and then you put it right here, and it'll tell you the stresses right at that, or sorry, the displacement at that point right there. And that's it. So you guys are going to create this model, and then basically you're just going to reanalyze it for different mesh sizes. So all you guys are going to do is you guys are going to come here, you're going to take your stress components, you're going to take your displacement components, you're going to go back to the model by clicking this button right here. Let's see if I get rid of this actually. You click this button right here to get back to the model. Actually, hold on, let's see if I can delete this really quick. I won't fool around with it. You go back to the model, you go back to the mesh tab, and you change your mesh, you rerun the analysis, you check it. So how do we get to that Mises toolbar, the von Mises stress? Are you asking about the von Mises stress? This toolbar up here will be there by default. So if you want the von Mises stress, you go down to S, and it'll be Mises by default. Does that answer your question? I'm not too sure what you're asking. Sorry. Which toolbar? Are you talking about the command that lets you see the stresses at a point? Because yes, that's actually down below here. Because I enlarged my screen, it enlarged all these things. If you guys stick around, because I know I'm running out of time, let me go back and I'll unenlarge my screen and I'll show you guys exactly what I'm talking about, just to make it nice and easy for you guys. So you guys can kind of see it's now more small, but at this very bottom one right here, this is called probe values. What you guys can do is you guys are going to click it. You guys will get this right here, and it'll give you guys the option to probe the elements or the nodes. Well, we're interested in the nodes, so we're going to click nodes, and from there we can select whatever we want. So because we're in the Mises right now, if I were to click on that point, it'll give me the von Mises stress as 29.47 MPa or whatever units. Now, if I were to exit out of this, and I were to go displacements, so down to U, and I were to go U2, I can go probe value again. I can hover over the point that I want, which is down here, and I see that my displacement is negative 0.049 units, basically. So does that make more sense? Perfect. And that's the assignment. You guys just repeat this a bunch of times with different mesh sizes and then different Poisson's ratios. So keep in mind that for the assignment, there's two different Poisson's ratios that I want you guys to explore, 0 and 0.3. So I got a direct message for the assignment. Are the number of elements to be varied along the length or keep them constant? So what I want you guys to do is just play around with the global mesh size. So keep your elements as square as possible and just vary that element size along here. So for instance, if I were to go back to my mesh, just keep playing around with this. So maybe select a global size of 1 to start, and then select a global size of 0.5, then 0.25, and then 0.125, etc., etc. So basically just keep decreasing the mesh size and plot the results as a function of the mesh size. As you guys will see, it'll start to converge upon a single value. Can I show you the probe again? Of course. So go back into the visualization. The probe value, where you get the values at the specific nodes, is down here at the very bottom. So I'm going to circle it a bunch of times because I know it's hard to see, but it's this button right here. We click it. This menu will pop up, and then we can click at any node that we want, and it'll be able to tell us what the displacement is. So if we want the displacement at this end node, I simply click, and it's negative 0.0496618 millimeters or whatever units you guys want. Good to go? Yeah, no problem. How was that? You guys excited to use ABAQUS? It's nice because you don't have to calculate the stiffness matrix at all. It does it all for you. Again, the whole point of today was to show you guys what exactly is happening inside each one of these elements. What should be handed in for the assignment? Great question. So the assignment should just be like your last one where you just submit one PDF file. If you guys want to show your model, just simply take a screenshot of whatever it is and submit it with. If we need your model, we will request it. So it should just be the results and screenshots of the model. Don't submit the model itself. We will request it if we need it.